Hello there, and welcome to Just About Earth, where curiosity gets cozy and science takes the scenic route toward rest. Tonight, we're going to wander back through a stretch of deep time when the planet felt warmer underfoot, when oceans reached into places that are now quiet plains, and when the air itself carried the quiet hum of a world very different from the one outside your window. If you've had a long day, or if your thoughts are still gently circling like leaves in a slow current, you might find this a comfortable place to let them settle. Before we drift too far, I'm quietly curious. Where are you listening from right now, and what time is it in your little corner of the world? Somewhere out there, night is just beginning. Somewhere else, morning light is slipping between buildings or over fields, and here we are, meeting in this shared moment, ready to step into a world that existed long before clocks, calendars, or even the idea of a tomorrow. If you find this calm exploration soothing, or if you enjoy letting your mind wander through old landscapes and gentle questions, you might consider liking the video or subscribing. It helps this small, peaceful corner reach others who might enjoy a soft place to rest their thoughts as well. Now, make yourself comfortable. Let your breathing slow just a little, not on purpose, but naturally, as it often does when you settle into a story. Because what we're about to explore is not just a list of facts or a parade of names, but a living, shifting planet moving through one of its most remarkable stretches of time. The Cretaceous Period is often remembered for its dramatic ending, but long before that final moment, it was an age defined by warmth, movement, and quiet transformation. Imagine a world where the continents were still in the middle of their long, patient drift, pulling away from one another like old friends slowly moving to different neighbourhoods. The familiar shapes of today's maps did not yet exist. North America and Europe were separated by widening waters. South America was beginning to loosen its connection to Africa. India was on a slow journey northward, like a traveller with no clear destination yet, destined for a future collision that would one day raise mountains. The seas were higher then, not just a little, but enough to spill into the hearts of continents. Shallow oceans covered large parts of what are now dry lands. In places that today might hold highways or quiet farmland, gentle waves once rolled back and forth, carrying schools of fish, drifting plankton, and the slow-moving bodies of marine reptiles through warm, sunlit water. These inland seas created long coastlines, where land and water met in wide, shifting boundaries. Life gathered in these places, as it often does where different worlds touch. The air itself felt different. Carbon dioxide levels were higher, and the planet held onto more heat. There were no ice caps at the poles, no vast sheets of frozen water reflecting sunlight back into space. Instead, forests reached far north and far south, growing in places that now see long, dark winters. The temperature difference between the equator and the poles was smaller, making the world feel more evenly warm, like a room where the heater has been left on just a bit too long. If you are somehow able to stand in this world, which of course you cannot, but if you let your imagination try, you might notice the thick, heavy feel of the air, the dense green of the landscape, and the constant, subtle motion of leaves, insects, and distant animals. The land was alive in a way that feels both familiar and strange. Familiar because life still followed patterns we recognise. Strange because the cast of characters was so different. One of the quiet revolutions of this time was happening close to the ground, in places that might not immediately draw attention. Flowering plants, which we now call angiosperms, began to spread across the land. Before this, much of the world's greenery was dominated by ferns, conifers, and other plants that did not produce flowers. They were successful in their own way, covering vast areas and forming the backbone of many ecosystems. But flowering plants brought something new. They offered colours, shapes, and scents that invited insects and other animals into a more direct relationship. This partnership changed landscapes slowly but deeply. As flowering plants spread, they created new kinds of food sources. Fruits, seeds, and nectar became part of the environment. encouraging the evolution of insects that could pollinate, birds that could feed, and animals that could carry seeds to new places. Fields and forests began to look different, not just in their shapes, but in how life moved through them. The world became more connected through these quiet exchanges between plants and the creatures that visited them. Somewhere nearby, larger shapes moved through the trees and open spaces. The dinosaurs so often imagined as a single, uniform group were actually a wide range of animals, each adapted to a specific way of living. There were massive plant eaters that moved in herds, using their size as both a shield and a tool. There were smaller, quicker hunters that relied on speed, sharp senses, and cooperation. Some dinosaurs were covered in simple feathers, not for flight, but for warmth, display, or communication. Birds, as we know them today, were beginning to take clearer form during this time. Their ancestors had already taken to the air, but now more recognizable bird-like features appeared. Feathers became more refined for flight. Bones grew lighter. Bodies became better balanced for life in the air. These early birds shared the skies with insects that had also been evolving alongside flowering plants, creating a busy, layered world above the ground, full of quiet flutters and sudden bursts of motion. Below the surface of the inland seas and along the open coasts, another kind of drama unfolded. Large marine reptiles moved through the water with slow, powerful strokes. Some had long necks and small heads, scanning the water for fish. Others were built more like living torpedoes, streamlined for speed and pursuit. Sharks and bony fish filled the spaces between, forming complex food webs that shifted with changes in temperature, sea level, and the movement of currents. Tiny organisms played a role just as important as the largest predators. Plankton, drifting near the surface, captured sunlight and turned it into energy, forming the base of ocean life. When these tiny organisms died, their remains sank to the seafloor, slowly building up layers of sediment. Over millions of years, these layers would become chalk and limestone, leaving a quiet record of ancient seas in the white cliffs and rocky hills we see today. On land, not all mammals were large or dominant. In fact, most were small, often no bigger than a modern squirrel or mouse. They lived in the shadows of larger animals, active mostly at night, feeding on insects, seeds, and whatever else they could find. Their world was one of hiding, quick movements, and constant awareness of danger. Yet within these small bodies, the foundations of future success were forming. Warm-blooded metabolism, varied teeth, and flexible behaviours would one day allow mammals to spread into nearly every environment on Earth. Volcanoes added another layer of motion to this already restless planet. In some regions, vast outpourings of lava covered the land, creating plateaus of dark, cooling rock. These eruptions released gases into the atmosphere, adding to the greenhouse effect and influencing climate over long periods. The planet breathed in these gases, held on to more heat, and slowly exhaled them through weathering, plant growth, and chemical reactions in the oceans. Even the magnetic field, invisible and often forgotten, played its part. Generated deep within the planet by the movement of molten metal in the core, this field shifted and wandered over time. It protected the atmosphere from the steady stream of charged particles coming from the sun, helping preserve the air and water that life depended on. Though no creature could see or feel it directly, it was another quiet companion in the long story of the Cretaceous world. If you follow the flow of time forward, gently and without hurry, you begin to notice patterns. Sea levels rise and fall as continents move, and the shape of the ocean basins changes. Climate warms and cools in response to shifts in gases, sunlight, and circulation. Life adapts, spreads, and sometimes fades away, making room for new forms. Nothing stands still for very long, even in an age that lasted for tens of millions of years. At some point in this long stretch, subtle changes began to stack up. The world was still warm, still green, still full of movement, but pressures were building. Volcanic activity increased in certain regions. ocean chemistry shifted as more carbon entered the water and air. Some ecosystems grew more fragile, more sensitive to disruption. These were not signs of an ending, not yet, but they were part of the same slow process that shapes all eras. As you imagine this world, try not to picture it as a single moment frozen in time. Instead, let it unfold like a long, unbroken day, where morning, afternoon and evening blend into one another. Forests expand and retreat. Coastlines creep forward and then pull back. Species appear, thrive, and quietly disappear, often without leaving more than a faint trace in the rocks below. And somewhere in this vast, shifting landscape, small, ordinary moments still happened. An animal pauses to drink from a shallow pool. A bird-like creature tests a new pattern of flight. A plant opens its flowers to the light for the first time. These are not the moments that make it into textbooks or museum displays, but they are the moments that make up the texture of a living world. As you settle deeper into this scene, notice how your own sense of time might be softening. The steady pace of deep history has a way of doing that, stretching your perspective far beyond minutes and hours. You might find your thoughts slowing, not because you're trying to slow them, but because the scale of what you're imagining invites a different kind of attention. Long before ice ever claimed the poles, before winds carried the bite of cold across open plains, the planet moved through a stretch of time where warmth was not an exception, but the rule. If you let your thoughts drift back into that distant world, you can begin to sense it not as a sharp, blazing heat, but as a steady, wrapping presence, like a blanket laid gently over land and sea alike. The Cretaceous climate did not shout its intensity. It hummed with it, quietly shaping every current of air, every drop of rain, and every living thing that depended on those invisible movements. The sky itself would have felt familiar in colour, still blue, still wide, still stretching from horizon to horizon, but the air it held was different in subtle, powerful ways. Carbon dioxide levels were higher than they are today, not by a small margin, but by several times. This extra carbon dioxide acted like a soft trap for heat, allowing sunlight to warm the surface and then holding that warmth close, rather than letting it escape back into space. The result was a planet where temperatures stayed elevated across nearly every region, from the equator to the farthest reaches of the north and south. You might imagine the equator as a place of relentless, overwhelming heat, but even there, the warmth was often balanced by moisture. Vast oceans fed the air with water vapour, which rose, cooled and fell again as frequent rain. Tropical regions were home to thick forests, wide wetlands, and slow-moving rivers that carried sediment from the land into the sea. The rain did not arrive in brief, violent bursts as it sometimes does in modern climates. Instead, it often came as long, steady showers that soaked the ground deeply, feeding roots and filling shallow lakes. Move away from the equator, and you would not find the sharp drop in temperature that defines the modern world. There were no icy barriers at the poles to mark the end of warmth. Instead, temperate conditions stretched far into high latitudes. Forests grew in places that today sit beneath snow and darkness for much of the year. Fossil evidence shows trees once stood in what is now the Arctic, their growth rings recording long, bright summers and winters that were cool, but not frozen. The idea of a polar forest can feel strange at first. Picture tall conifers and broad-leaved plants rooted in soil that, millions of years later, would lie beneath permafrost. In the Cretaceous, these regions still experienced the long cycles of light and dark caused by Earth's tilt, but the temperatures remained mild enough for plant life to survive through the darker months. Instead of snow piling up, there may have been cool rains, mist, and slow-moving clouds drifting low over the landscape. Oceans played a central role in keeping this warmth evenly distributed. The shape of the continents and the wide, open connections between seas allowed currents to flow freely around the globe. Warm water from the equator travelled toward the poles, carrying heat with it like a slow, steady delivery system. Cooler water returned toward lower latitudes. creating a continuous exchange that softened temperature differences across the planet. These ocean currents did more than move heat. They also carried nutrients, oxygen, and life. In some regions, upwelling brought deep, nutrient-rich water to the surface, fueling blooms of plankton that formed the base of entire marine ecosystems. In other areas, warm, shallow seas spread across continental interiors, creating broad, sunlit environments where reefs, shellfish, and fish thrived. Sea levels during much of the Cretaceous were significantly higher than today. Without large ice sheets to lock up water at the poles, more of the ocean remained free to cover the land. Shorelines moved inland, sometimes by hundreds of kilometres. This created long, winding coasts and shallow seas that cut continents into smaller pieces. North America, for example, was split by a vast inland sea that connected the Arctic Ocean to the Gulf of Mexico, turning what we now see as a single landmass into two long, narrow continents separated by water. These shallow seas acted like enormous heat reservoirs. Sunlight could easily penetrate the water, warming it from the top down. That warmth was then released back into the air, especially at night, preventing temperatures from dropping too far. The result was a climate that felt steady rather than extreme, even in places far from the equator. Wind patterns followed this warmth and moisture. Large-scale circulation carried air masses around the globe, shaping where rain fell and where drier conditions took hold. In some regions, long stretches of dry weather created open landscapes dotted with hardy plants that could survive with less water. In others, constant moisture supported dense forests and swamps where fallen leaves and plant matter built up into thick, dark soil. The rhythm of seasons still existed, guided by Earth's orbit and tilt, but it was gentler in many places. Summers were warm, often very warm, but winters were mild by modern standards. Frost, where it appeared at all, was likely rare and short-lived outside of high mountains. This softer seasonal cycle allowed plants to grow for longer periods each year, extending the time available for photosynthesis and growth. Plants responded to this opportunity with energy. Flowering plants spread into new territories, competing with older groups like conifers and ferns. Their ability to grow quickly, produce seeds protected by fruits, and form partnerships with insects gave them an edge in many environments. Fields of low-flowering plants may have filled open spaces, while trees with broad leaves created layered canopies that filtered sunlight into shifting patterns on the ground below. These green landscapes did not just provide food, they also shaped the climate in return. Plants absorbed carbon dioxide from the air during photosynthesis, storing it in their tissues and in the soil when they died and decayed. Over long periods, this process helped regulate the amount of carbon in the atmosphere, acting as a slow, natural balancing system. In wetlands and shallow seas, plant matter that was buried under sediment could eventually become coal, oil, or gas, locking carbon away for millions of years. Volcanic activity added another layer of influence. In several parts of the world, massive volcanic provinces erupted over long stretches of time, releasing lava and gases across vast areas. Carbon dioxide and sulfur compounds entered the atmosphere, sometimes warming the planet further, sometimes creating temporary cooling by forming particles that reflected sunlight. These volcanic episodes did not happen all at once. They unfolded in pulses, each one nudging the climate in slightly different directions. The air, rich in moisture and warmth, carried storms across oceans and continents. These were not necessarily the towering, violent storms we often picture today, though those may have occurred as well. Many would have been long-lasting systems, drawing energy from warm seas and releasing it as steady rain over wide areas. Rivers swelled and shrank in response, carving valleys, depositing sediment, and slowly reshaping the land. Mountains, too, played their part. As tectonic plates collided and slid past one another, ranges rose in some regions, altering wind patterns and creating rain shadows. One side of a range might receive heavy rainfall as moist air was forced upward, while the other side remained relatively dry. These contrasts added variety to the landscape, creating a patchwork of environments within the broader warmth of the global climate. Life adapted to these patterns in countless ways. Large plant-eating animals followed the growth of vegetation, moving with the seasons or staying within regions where food remained available year-round. Predators tracked these movements, shaping their own ranges around the paths of their prey. Birds and insects followed flowering cycles, spreading pollen and seeds as they went. Even small changes in temperature or rainfall could ripple through these systems. A slightly drier season might reduce plant growth, affecting herbivores and, in turn, the animals that depended on them. A wetter period could expand wetlands, creating new habitats for amphibians, fish, and insects. The climate was not a static backdrop. It was an active participant in the daily life of the planet. One of the most interesting aspects of this warm world is how evenly it seemed to distribute its heat. Modern climates are defined by strong gradients, with hot tropics and cold poles. The Cretaceous appears to have softened this contrast. This does not mean the poles were tropical, but the difference between low and high latitudes was smaller. This allowed similar types of ecosystems to appear across wide ranges of the globe. Imagine travelling from what is now a mid-latitude region toward the north. Instead of watching forests gradually give way to tundra and ice, you might see forests continue, slowly changing in species but not disappearing altogether. The trees might grow more slowly, their shapes might shift, but the landscape would remain green and alive. The ocean floor tells part of this story as well. Layers of sediment reveal periods of high biological productivity, where warm, nutrient-rich waters supported massive populations of microscopic organisms. When these organisms died, they settled to the bottom, forming thick deposits that now appear as chalk cliffs and limestone beds. These rocks are quiet records of ancient seas and the climate that sustained them. Weathering on land also left its mark. Warm, wet conditions tend to break down rocks more quickly, turning them into soil. This process, carried out by water, temperature changes and living organisms, created deep, fertile soils in many areas. These soils supported dense plant growth, which in turn supported complex food webs. Clouds, often overlooked, were constant companions in this world. Warm air rising from the surface carried moisture upward, forming layers of cloud that reflected some sunlight back into space while trapping heat below. This balance influenced how much energy reached the ground and how much stayed in the atmosphere. Over time, shifts in cloud cover could slightly cool or warm regions, adding another variable to an already complex system. The longer you sit with this picture, the more you can see the climate not as a single, simple condition, but as a web of relationships. Sunlight warms the surface warms the air and water move, carrying heat and moisture. Plants and animals respond to these movements, and in responding they change the atmosphere and the land. The cycle continues, turning slowly but constantly. There were moments of change even within this long warm age. Geological evidence points to periods when temperatures rose higher, sometimes called thermal maxima. During these times, the planet became even warmer, seas expanded further, and some ecosystems were pushed to their limits. At other times, slight cooling occurred, pulling shorelines back and allowing new land to emerge. These shifts did not happen overnight. They unfolded over hundreds of thousands or millions of years, slow enough that life could often adapt, but not always without loss. The idea of a softer planet does not mean a gentle one in every sense. Life still faced challenges. Droughts, floods, storms, and volcanic winters could all disrupt local environments. Predation, competition, and disease-shaped populations just as they do today. The softness lies more in the absence of extreme cold, in the way warmth wrapped the globe and allowed green landscapes to stretch into places we now think of as harsh and unwelcoming. If you imagine standing somewhere near one of these ancient coasts, you might feel a warm breeze coming off the water, carrying the scent of salt and vegetation. The tide would move in and out across a wide, shallow shelf, leaving behind pools where small creatures darted and plants rooted themselves in shifting sand. Inland, forests would rise in layers, from low shrubs and flowering plants to tall trees whose leaves filtered the sunlight into a moving pattern on the ground. Above, clouds would drift slowly, their shapes changing without hurry. Rain might fall later in the day, not as a sudden event but as a gradual darkening of the sky, followed by the soft, steady sound of water on leaves and soil. Streams would swell, carrying fresh sediment toward the sea, adding another thin layer to the ever-growing record of the planet's surface. All of this happened without any sense of an approaching end. The climate did not carry a warning sign or a countdown. It simply continued, shaped by forces deep within the earth and far beyond it. The sun shone, continents moved, oceans flowed, and life adapted day after day, year after year, for millions of years. As you let this warm, green world settle in your mind, you might notice how it contrasts with the sharp, often hurried feel of the modern world. There is no schedule here, no clock measuring out the hours. The changes are slow, almost imperceptible in any single moment. Yet over long stretches they transform everything. And as we stay with this sense of steady warmth and gentle movement, it becomes easier to see how the climate of the Cretaceous was not just a background condition, but a guiding presence. It shaped where forests grew, where seas spread, and how animals moved across the land and through the water. It set the stage for the interactions between plants and insects, between predators and prey, between land and ocean. Long after the warmth of the air and the steady rhythm of rain had shaped the surface of the planet, there was another kind of movement unfolding far below, one so slow and quiet that no living thing could ever feel it in a single lifetime. The ground beneath forests, rivers, and shallow seas was not as solid and unmoving as it might have seemed. Instead, it rested on enormous plates of rock that drifted across the softer layer beneath them, carried along by the deep, patient flow of heat from the Earth's interior. During the Cretaceous, this hidden motion was steadily rearranging the face of the world. If you imagine the continents as pieces of a puzzle laid out on a table, the Cretaceous was a time when many of those pieces were sliding away from one another, opening new gaps that filled with water and nudging into positions that would eventually become familiar to us. The supercontinent that once held most of the land together had already begun to break apart earlier, but now the process was well underway, shaping coastlines, redirecting oceans and creating long, winding boundaries between land and sea. One of the most noticeable changes was happening in the space between what we now call North America and Europe. The Atlantic Ocean was opening wider, not in a dramatic rush, but in a steady pull that added a few centimetres of distance each year. Over millions of years, those small increments added up to a vast stretch of water, turning what had once been neighbouring lands into continents separated by rolling seas. As the ocean basin widened, new crust formed along a long underwater ridge where molten rock rose, cooled and hardened, adding fresh surface to the planet. South America and Africa were also moving apart, though in the Cretaceous they were still close enough to share similar plant and animal life. Their separation created new coastlines that faced one another across a growing ocean, each shaped by waves, tides, and the slow erosion of wind and rain. Rivers carried sediment from the interior of the continents to these coasts, building deltas and sandy plains that shifted with every change in sea level. India was on its own remarkable journey. Once part of a southern landmass, it had broken free and begun moving northward across a wide stretch of ocean. It travelled faster than most continents do, pushed along by the forces beneath it, heading toward a future collision with Asia that would one day raise the Himalayas. During the Cretaceous, this journey created new seafloor behind it and altered ocean currents around it, influencing climate and marine life along its path. Far to the south, Antarctica was not yet the frozen continent we know today. it was still connected to Australia and South America, forming a broad southern landmass surrounded by cool but not icy seas. Forests grew there, and rivers flowed across ground that would later lie beneath kilometres of ice. As the connections between these southern continents weakened, new passages began to open, allowing ocean water to circulate in different patterns. These shifting patterns of water movement had wide-reaching effects. Ocean currents act like conveyor belts, carrying heat, salt, and nutrients around the globe. When a new seaway opened or a shallow passage closed, it could redirect these currents, warming some regions and cooling others. During the Cretaceous, the changing layout of continents allowed warm equatorial waters to travel more freely toward the poles, helping maintain the gentle temperature differences we explored earlier. On land, the movement of plates created mountains in some places and flattened landscapes in others. Where plates collided or scraped past one another, the crust crumpled and thickened, pushing rock upward into long ranges. These rising areas altered local climates by forcing air to rise, cool, and drop its moisture as rain on one side, leaving the other side drier. Over time, this created patterns of wet and dry regions that influenced where forests, grasslands, and deserts formed. In other regions, the crust stretched and thinned as plates pulled apart. This could create long valleys and low-lying basins that filled with water or sediment. Some of these basins became inland seas, like the one that once split North America into eastern and western halves. This vast body of water, warm and shallow, connected the Arctic to the Gulf of Mexico, allowing marine life to move freely between northern and southern oceans. The edges of continents, known as continental margins, were especially active places. Waves and tides constantly rework these boundaries, while the slow sinking or rising of the land, called subsidence and uplift, changed how far the sea reached inland. A coastline might creep forward for thousands of years, only to retreat again as the balance between sea level and land height shifted. These changes were not uniform across the globe. Some regions experienced rapid geological activity, with frequent earthquakes and volcanic eruptions. Others remained relatively stable, their landscapes changing mainly through erosion and the slow build-up of sediment. The planet, even then, was a patchwork of restless and quiet zones, each contributing its own piece to the overall shape of the world. Volcanoes, often tied to the boundaries between plates, played a particularly dramatic role. In some areas, long cracks in the crust allowed lava to pour out over enormous areas, creating vast plateaus of dark rock. These events did not usually happen in a single explosion. Instead, they unfolded over long periods, with repeated flows covering older layers and gradually building thick stacks of solidified lava. The gases released during these eruptions entered the atmosphere, influencing climate as we discussed earlier, but they also left marks on the land itself. Ash settled over wide regions, sometimes creating fertile soil after it broke down. Lava flows reshaped river paths, blocked valleys, and created new high ground that altered how water moved across the surface. Rivers responded quickly to these changes. If a region was uplifted, rivers cut deeper into the rock, carving canyons and carrying fresh sediment downstream. If land sank or sea levels rose, rivers slowed, dropped their loads of sand and mud, and built wide, flat floodplains. Over time, these processes created layered landscapes, with old river channels buried beneath newer ones, preserving a record of past environments in the rock. The shape of the continents also influenced the paths of storms and prevailing winds. Large land masses heat and cool differently than oceans, creating pressure differences that drive air movement. As continents shifted, these patterns changed, altering where rain fell and where dry conditions took hold. A region that was once a lush forest might slowly transition into a more open landscape as wind patterns shifted and rainfall decreased. Plants and animals followed these changes. When a new land bridge formed or a shallow sea closed, species could move into new territories, When a connection disappeared, populations became isolated, evolving in different directions over time. This process, known as vicariance, played a major role in shaping the diversity of life during the Cretaceous. You can see traces of this today in the distribution of fossils. Similar species appear on continents that were once connected, even if they are now separated by vast oceans. These patterns act like quiet footprints, marking the paths that land and life once shared. The seafloor too tells a story of movement. Magnetic minerals in newly formed ocean crust align themselves with Earth's magnetic field as they cool. Because the magnetic field has flipped direction many times over geological history, these minerals create a striped pattern on the seafloor, recording the timing of crust formation. During the Cretaceous, these stripes were being laid down along long ridges, marking the steady expansion of ocean basins. Beneath the surface, deep within the mantle, heat continued to rise and fall in slow currents. These currents, though invisible, were the engine behind all this motion. They transferred energy from the core toward the crust, driving plates apart in some places and pushing them together in others. This internal circulation operated on timescales far beyond any single era, yet its effects were written across every mountain range, basin and coastline. If you try to picture the world from far above, as if you were watching it from a great distance, you might see the continents as slow-moving shapes, gliding across a surface that seems almost fluid when viewed over millions of years. Oceans open like widening cracks. Seas fill low-lying areas. Land masses drift closer or farther apart, changing the geometry of the planet. This changing shape influenced how life experienced the world. An animal that lived near the coast might find its home gradually moving inland as sea levels fell or drifting closer to the water as they rose. A plant adapted to moist conditions might spread across a new lowland created by subsidence, while one that preferred drier ground might retreat to higher areas as wetlands expanded. Even the smallest creatures were affected. Insects that relied on certain plants followed their hosts as landscapes changed. Freshwater fish adapted to river systems that were constantly being reshaped by uplift and erosion. Marine species moved with shifting coastlines and changing depths, finding new habitats in newly formed bays and shelves. Time, in this context, feels different. The movement of a continent by a few centimetres each year is something you would never notice in a lifetime. Yet over the span of the Cretaceous, which lasted tens of millions of years, those tiny steps carried land masses across thousands of kilometres. It is a reminder that slow processes given enough time can produce the most dramatic changes. There were moments when this slow dance left more sudden marks. Earthquakes, though rarely preserved directly in the fossil record, would have shaken landscapes and altered river courses. Landslides might have reshaped hillsides. Volcanic eruptions could temporarily darken skies and cover large areas with ash. These events added punctuation to an otherwise steady sentence of geological change. The interaction between land and sea was especially dynamic. As continents drifted and sea levels rose and fell, shallow marine environments expanded and contracted. These areas, rich in life, were among the most productive on the planet. They supported reefs, shellfish, fish, and countless microorganisms. When they disappeared, life had to move or adapt, sometimes leading to bursts of evolution as new niches opened up elsewhere. Inland, broad plains formed in areas where sediment built up over long periods. These plains were often crossed by braided rivers that shifted their channels frequently, creating a mosaic of wet and dry areas. Such environments supported a wide range of plants and animals, from towering trees to small burrowing mammals. Mountains, though often associated with dramatic peaks, also influenced the world in quieter ways. They acted as sources of rivers, collecting moisture from the air and releasing it as streams and snowmelt. The minerals eroded from their slopes enriched soils downstream, supporting plant growth far from the original rock. As you let these images settle, you can begin to sense the Cretaceous world as a place in constant gentle motion. Not just in the movement of animals and the flow of water, but in the slow, persistent shifting of the ground itself. The planet was, and always has been, an active participant in its own story. This perspective can make the modern world feel like just one frame in a very long film. The continents beneath your feet are still moving, still following the same deep currents that guided them millions of years ago. The shape of the world you know is temporary, part of a longer sequence that began long before the Cretaceous and will continue long after. During that ancient time, life had no awareness of these grand patterns. A dinosaur grazing in a floodplain did not know the land beneath it was slowly rising. A fish swimming in a shallow sea did not sense that the seaway connecting it to another ocean would one day close. Yet these unseen changes shape their futures all the same. It becomes easier to see how the climate, the landscapes, and the living world were all connected. The drift of continents influenced ocean currents. Those currents shaped temperature and rainfall. Climate guided where plants grew. Plants supported animals. Animals moved seeds, stirred soil, and influenced vegetation in return. Nothing happened in isolation. Each slow shift set off a chain of responses that rippled across the planet. The world of the Cretaceous was not a static stage where life played out its roles. It was a moving, changing system where the stage itself was part of the performance. If you follow the slow reshaping of the land and let your attention drift back down from the wide view of moving continents, you begin to notice what filled the spaces those continents created. The warmth of the air, the steady presence of moisture, and the rich soils formed by erosion and volcanic ash gave rise to landscapes that felt full, layered, and deeply alive. During this stretch of time, the land did not simply wear a coat of green. It grew forests of many kinds, spread open plains, and nurtured one of the quietest but most far-reaching changes in the history of life on Earth. Before flowering plants became common, much of the world's vegetation was dominated by older groups. Ferns unfurled their fronds in damp, shaded places. Conifers stood tall with needle-like leaves, releasing pollen into the wind. Cycads, with their sturdy trunks and stiff crowns of leaves, gave some landscapes an almost palm-like appearance. These plants had been shaping ecosystems for millions of years, and they were well adapted to the warm, moist climate of the Cretaceous. Forests built from these species could be dense and towering, with high canopies and dim, cool understories where smaller plants clung to the filtered light. But change was already moving through these green spaces, not as a sudden replacement, but as a gradual weaving in of something new. Flowering plants, which had appeared earlier in small numbers, began to spread more widely. At first, they were often low-growing, living near the edges of forests, along riverbanks, and in open, disturbed areas where sunlight reached the ground more easily. These were places shaped by floods, shifting channels, or falling trees, where the landscape was in constant motion and opportunity appeared in small patches. What set these plants apart was not just the presence of flowers, but the way those flowers reshaped relationships between living things. Instead of relying only on wind to carry pollen from one plant to another, many flowering plants began to form partnerships with animals. Insects drawn by colour, scent, and nectar moved pollen as they fed. This made reproduction more efficient and allowed plants to spread into new areas more quickly. As these plants became more common, they began to influence the structure of entire landscapes. Fields of low, flowering vegetation appeared in open areas, creating mosaics of colour and texture that shifted with the seasons. Along rivers, shrubs and small trees with broad leaves formed thick borders that stabilised banks and shaded the water. In forest understories, flowering plants filled gaps beneath taller trees, adding layers of growth where once there might have been bare ground or ferns alone. The rise of these plants did not push the older groups aside overnight. For a long time, conifers, ferns and cycads continued to dominate many forests, especially in regions where conditions favoured their slower, steady growth. What changed was the variety within those forests. Instead of a few types of plants forming the bulk of the vegetation, landscapes began to host a broader mix of species, each occupying its own space in the light, soil and moisture available. This increase in variety had effects that reached far beyond the plants themselves. Insects, for example, found new sources of food and new roles to play. Some became specialized pollinators, visiting only certain types of flowers. Others fed on leaves, stems, or seeds, shaping plant populations through their appetites. Over time, this back and forth between plants and insects drove changes in both groups, leading to new forms, behaviors, and relationships. Birds too found opportunities in these changing landscapes. Fruits and seeds provided new kinds of nourishment. Dense shrubs offered nesting sites and shelter. The spread of flowering plants created corridors of food and cover that allowed birds to move across larger areas, linking different habitats together. On the ground, small mammals took advantage of these new resources as well. Seeds and fruits could be gathered, stored, and eaten, supporting animals that were able to move quickly, hide easily, and make use of patchy environments. Some mammals likely played a role in spreading plants by carrying seeds away from the parent plant, either in their mouths or through their digestive systems. As forests grew taller and more layered, they created a range of micro-environments. The canopy, high above the ground, was a place of light, wind, and movement. Leaves there faced the full strength of the sun and the passing of clouds. Below, the understory was cooler and darker, with light arriving in shifting patches that moved across the forest floor as the day passed. Near the ground, the air was often still and damp, carrying the scent of soil and decay. Each of these layers supported different forms of life. Some animals moved through the treetops, feeding on leaves, insects, or fruit. Others stayed closer to the ground, foraging among fallen leaves and roots. Decomposers, like fungi and bacteria, worked quietly in the soil, breaking down dead plant material and returning nutrients to the earth. This recycling process kept the system running, ensuring that growth could continue year after year. In wetter regions, forests gave way to swamps and wetlands. Here, water covered the ground for much of the year, creating soft, muddy soils where specialized plants took hold. Tall, reed-like vegetation and water-loving trees formed thick stands that slowed the movement of water, trapping sediment and building up layers of organic material. Over long periods, these layers could become deep deposits of peat, storing carbon and shaping the landscape in subtle ways. Rivers acted as moving lines of connection through all of this. They carried water, sediment, and nutrients from high ground to the sea, cutting paths through forests and plains alike. Along their banks, plant growth was often especially lush, supported by regular flooding that refreshed the soil. These river corridors became pathways for animals as well, allowing them to travel through different environments while staying close to water and food. Open areas, where trees were sparse or absent, formed in places shaped by fire, flooding, or dry conditions. In these spaces, low-growing flowering plants and grasses-like species spread out, creating broad, sunlit fields. These areas supported large plant-eating animals, which could move in groups across the open ground, feeding on abundant vegetation. The presence of these large animals in turn shaped the plants. Heavy footsteps compacted soil in some places and broke it open in others. Grazing kept some plants short and allowed others to grow taller. Seeds could be carried in fur or dropped far from where they first sprouted. The landscape became a conversation between plants and animals, each influencing the other's form and distribution. Trees in the Cretaceous forests often grew to impressive sizes. Warm temperatures and long-growing seasons allowed them to add layer upon layer of wood year after year. Some conifers and broadleaf trees formed massive trunks and wide canopies, creating landmarks in the landscape that could be seen from far away. Beneath these giants, younger trees and shrubs competed for light, growing tall and straight in the shade, waiting for a gap to open above them. When a large tree fell, whether from age, storm, or the gradual weakening of its roots, it created a sudden opening in the forest. Sunlight poured in, warming the soil and triggering a burst of growth. Flowering plants, quick to take advantage of these conditions, often moved in first, followed by young trees. Over time, the gap would close again, becoming part of the larger forest. This cycle of growth, fall, and renewal added a dynamic quality to even the most established landscapes. In regions closer to the coast, salt-tolerant plants formed communities in tidal zones and shallow lagoons. These plants stabilized muddy shores and created sheltered areas where small animals could feed and hide. As sediment built up, new land emerged, allowing more vegetation to take root. The boundary between land and sea was constantly shifting, shaped by waves, currents, and the slow rise or fall of the ground itself. High in some regions, mountains created their own set of conditions. Slopes faced the sun at different angles, creating warm and cool sides. Rain fell more heavily on one side of a range than the other, producing wet forests in some valleys and drier, more open landscapes in others. This variation allowed different plant communities to exist close together, adding to the overall diversity of the region. The spread of flowering plants also began to change the chemistry of the soil. Leaf litter from these plants broke down differently than that of many older groups, influencing the mix of nutrients available to roots and microbes. Over time, this affected which plants could thrive in certain areas, reinforcing the presence of flowering species in many environments. These changes did not happen everywhere at the same time. Some parts of the world saw a rapid increase in flowering plants, while others remained dominated by conifers and ferns for much longer. Climate, soil type, and the presence of animals all played a role in determining how quickly these new plants took hold. The landscape, then, was not a single uniform scene, but a patchwork. Dense forests stood next to open plains, wetlands merged into river valleys, coastal zones shifted with the tides. Within this patchwork, life moved, adapted and diversified, finding new ways to make use of the space and resources available. If you imagine walking through one of these Cretaceous forests, you might notice the weight of the air, warm and carrying the scent of leaves and damp soil. The ground beneath your feet would be soft in places, covered in fallen foliage and the remains of older plants. Light would filter down through layers of leaves, creating patterns that moved slowly as clouds passed overhead. You might hear the movement of insects in the undergrowth, the rustle of larger animals moving through the trees, and the distant sound of water flowing somewhere nearby. The forest would feel full, not just of life, but of motion, even in moments when nothing obvious was happening. Beyond the trees, open areas would stretch out bright under the sun, dotted with low plants and flowering patches. Here, the view would be wider, the sky more visible, and the sense of space more pronounced. Animals moving across these plains would be easier to spot, their shapes standing out against the vegetation. All of this was made possible by the combination of climate, geology, and biology that defined the Cretaceous. Warm temperatures allowed plants to grow across wide ranges. Moving continents created new spaces and connections. Flowering plants introduced new ways for life to interact and spread. The result was a world that felt rich in possibility, where landscapes were not just backdrops, but active participants in the story of life. Every river bend, forest edge, and open field was shaped by forces both deep within the earth and high in the sky. As you hold this image of forests layered with life and open spaces dotted with new growth, it becomes easier to see how the rise of flowering plants was not just a botanical event. It was a shift in how the land itself functioned, how animals moved through it, and how energy flowed from sunlight into leaves, into bodies, and back into the soil. Somewhere above the warm forests and winding rivers of the Cretaceous world, movement began to take on a new dimension, not just forward or sideways, but upward, into the open space between the ground and the clouds. This was not the sudden appearance of perfect flight, not a dramatic leap from earth to sky, but a long, careful experiment carried out by countless small bodies, each one testing how far it could go beyond the limits of running and jumping. Feathers had already been part of this world for a long time. They did not begin as tools for flying. Early on, they likely served simpler purposes, helping small, active animals regulate their body temperature, making them more efficient at staying warm during cooler nights or in shaded forests. Feathers also played a role in communication. Patterns, colours, and shapes could signal health, readiness to mate, or even warnings to rivals. In a world dense with life, being seen and recognised mattered. These early feathered animals were not birds in the modern sense. They were part of a wider group of dinosaurs, many of them small, light-bodied, and quick. Their skeletons were built for speed and agility, with long legs, flexible spines, and arms that could move in wide arcs. Feathers covered their bodies in various forms, from simple, hair-like filaments to more complex structures with a central shaft and branching barbs. Over time, these feathers began to interact with the air in useful ways. When an animal ran, jumped, or fell from a branch, the feathers on its arms and tail created drag. This slowed its descent, giving it more control over where it landed. Even a small advantage could make a difference, turning a dangerous fall into a manageable glide. Life in the Cretaceous forests offered plenty of opportunities to climb, leap, and scramble. Trees grew tall, their branches forming a layered network of pathways. Small animals moved through this space in search of insects, seeds, and safety from larger predators on the ground. In this environment, the ability to move between branches or to descend quickly without injury would have been valuable. As generations passed, small changes in bone shape, muscle attachment, and feather structure added up. Arms grew longer in relation to the body. Feathers on those arms became broader and more organised, forming surfaces that could push against the air. The tail, once a long, bony counterbalance, shortened and became lighter, with feathers taking over much of its role in steering and balance. These changes did not follow a single straight path. Different lineages tried different solutions. Some animals developed strong hind legs and used their wings mostly for balance and display. Others became better gliders, spreading their feathered arms wide to travel between trees or down slopes. A few began to experiment with powered movement, flapping their arms to gain lift, even if only for short bursts. The idea of the first bird can be misleading. There was no clear moment when one kind of animal suddenly became another. Instead, there was a long overlap, a blending of features we now associate with dinosaurs and birds. Some creatures had teeth, clawed fingers on their wings, and long, bony tails, but also feathers and the ability to glide or flap. Others had more bird-like bodies, with lighter skeletons, fused bones, and feathers shaped specifically for flight. Fossils from this period show an incredible variety of these forms. Some were small and sparrow-sized, flitting through the undergrowth. Others were larger, with wingspans that stretched wider than a person is tall. Their feathers came in different shapes and in some cases different colours, hinting at a visual world richer than the grey and brown tones we often imagine for ancient animals. The structure of the feather itself became more refined over time. A modern flight feather is a complex tool with a stiff central shaft and tightly interlocking barbs that form a smooth, flexible surface. This design allows air to flow over the wing in a way that creates lift, while still being light enough not to weigh the animal down. During the Cretaceous, this kind of feather was becoming more common, especially in lineages that spent more time in the air. Bones changed alongside feathers. The skeletons of early birds and their close relatives show signs of lightening. Some bones became hollow, filled with air sacs connected to the lungs. This reduced weight without sacrificing strength. The breastbone or sternum began to develop a keel, a ridge of bone where powerful flight muscles could attach. These muscles allowed for stronger, more sustained flapping. Breathing itself took on a new form, the air sac system found in birds today, which allows for a continuous flow of air through the lungs, likely began to develop during this time. This system is more efficient than the simple in and out breathing of many other animals, supporting the high energy demands of flight and active lifestyles. While some lineages took to the sky more fully, others remained closer to the ground, using their feathered arms for balance, display, or short, controlled jumps. The diversity of these forms suggests that the air was not claimed by a single group all at once. Instead, it became a shared space, with different animals using it in different ways. Insects were already there, of course, filling the air with their own patterns of flight. The rise of flowering plants had supported a wide variety of flying insects, from beetles and flies to early bees and butterflies. These insects provided a ready food source for small, agile hunters that could follow them into the air or catch them as they moved between flowers. This relationship between plants, insects, and early birds created a new kind of network. Flowers attracted insects. Insects attracted feathered predators. Predators in turn influenced which insects thrived and which did not. The movement of these animals also helped spread pollen and seeds, linking the sky to the ground in subtle but important ways. Waterways offered another stage for this unfolding story. Along rivers, lakes, and coastal shallows, some early birds and bird-like animals hunted fish and small aquatic creatures. Long legs allowed them to wade through shallow water. Narrow beaks, sometimes lined with small teeth, helped them grip slippery prey. Wings provided not just flight, but also balance as they moved across uneven ground and water. The skies themselves were not empty, even before birds became more common. Flying reptiles, known as pterosaurs, had been part of the air for a long time. They range from small insect-eating forms to massive creatures with wingspans wider than many modern airplanes. During the Cretaceous, these reptiles still dominated some parts of the sky, especially in coastal and open environments. The presence of pterosaurs likely influenced how early birds evolved. Competition for food and space in the air would have shaped where and how these different groups flew. Smaller birds may have focused on forested areas and inland habitats, where pterosaurs were less common, while larger pterosaurs took advantage of open skies and coastal winds. The forests themselves offered shelter and opportunity. Branches, leaves, and trunks created a complex three-dimensional space, where agility and precise movement mattered more than raw speed or size. In this environment, smaller, more maneuverable flyers could thrive, darting between obstacles and landing in tight spaces. Nesting behaviour also began to take shape. Some early birds likely built simple nests in trees, on cliffs, or on the ground, using plant material to cushion their eggs. Others may have laid eggs in sheltered spots without much preparation. The act of caring for eggs and young added another layer to their lives, tying them to specific places for parts of the year. Feathers played a role here as well, providing insulation for eggs and hatchlings. Warm bodies and feathered coverings could keep young animals at a stable temperature, increasing their chances of survival. This kind of care required time and energy, but it also allowed for more complex behaviours and social interactions. Sound entered the picture in new ways. Modern birds are known for their calls and songs, used to attract mates, defend territory, and communicate with others. While we cannot hear the voices of Cretaceous birds, their anatomy suggests that some form of vocalization was likely present. The development of a syrinx, the specialized vocal organ in birds, may have begun around this time, adding another dimension to how these animals interacted with their world. As these feathered creatures spread, they carried their influence across different environments. In dry regions, they moved between scattered trees and shrubs. In wetlands, they waded and flew over shallow water. In coastal zones, they followed the line where land met sea, feeding on both terrestrial and marine life. Their movements connected distant places. A bird that flew from one forest to another could carry seeds stuck to its feathers or in its digestive system. Insects caught in one area might be transported to another. Even small actions like these help shape the distribution of plants and animals across the landscape. The long-term impact of this shift toward flight is hard to overstate. The ability to move quickly and easily across barriers like rivers, mountains, and open spaces changed how species spread and interacted. It allowed for faster responses to changes in climate and landscape. It opened up new ecological roles that had not existed before. Yet, in the Cretaceous, this was still an unfolding story. Birds, as we would recognize them today, were becoming more common, but they were not yet the dominant group they would later become. They shared their world with many other forms, some of which would not survive the changes still to come. The fossil record from this time shows both success and experimentation. Some lineages flourished, spreading across wide areas. Others appeared briefly and then vanished, leaving behind only fragments of bone and feather pressed into stone. Each one represents a different approach to the same challenge, finding a way to live in a world that offered both opportunity and danger. The sky, in this sense, was not a single domain to be conquered. It was a new layer of the environment, one that animals were gradually learning to use. Some skimmed its edges, some embraced it fully. Others touched it only in brief moments, leaping or gliding before returning to the ground. If you imagine standing in a Cretaceous landscape and looking up, you might see shapes moving across the light. Small, quick silhouettes darting between trees, larger forms gliding in wide circles over open water, insects flickering in and out of view, catching the sun on their wings. The air would feel busy, alive with motion that mirrored the life below. This connection between ground and sky created a sense of vertical depth in the environment. Life was no longer confined to the surface and the water. It occupied layers, from the soil to the canopy to the open air above. Each layer supported its own communities, linked by the movements of animals that crossed between them. As this layered world developed, it changed how energy flowed through ecosystems. Sunlight fed plants. Plants fed insects and herbivores. Insects and small animals fed birds and other predators. The ability to fly allowed some of these connections to stretch over greater distances, smoothing out local shortages and spreading abundance more widely. Over long periods, these patterns became part of the structure of the planet's living systems. They added resilience in some places, allowing life to recover more quickly from local disruptions. In other places, they created new dependencies, where the loss of one group could ripple through many others. The story of feathers and wings during the Cretaceous is, at its heart, a story of possibility. It shows how a simple structure, first used for warmth or display, can open the door to entirely new ways of living. It reminds us that major changes often begin with small steps, repeated over long spans of time. As you let this image of a sky slowly filling with life settle, you might notice how it changes the feel of the world below. Forests become not just places to walk through, but places to move above. Rivers become lines that can be followed from the air. Open plains become spaces to cross in moments rather than days. This shift sets the stage for new kinds of interactions, new forms of hunting and hiding, and new ways for animals to shape the land and each other. And while the air has begun to play a larger role in the story of life, the ground and the water remain just as important, filled with their own dramas and quiet processes. Across the wide sunlit plains and through the deep layered forests of the Cretaceous, the most visible presence was not in the air or beneath the waves, but on the land itself. The ground carried the steady weight of bodies that had, by this time, become the dominant forms of large life on Earth, their footsteps pressed into soft soil, riverbanks and coastal sands, leaving marks that would sometimes be filled by sediment and preserved for millions of years. This was an age when dinosaurs were not rare or exceptional. They were the everyday giants of their world, shaping the landscape simply by existing within it. To think of this period as a single reign can make it sound uniform, as if one kind of creature ruled over all others in the same way everywhere. The reality was far more varied. Dinosaurs during the Cretaceous were spread across nearly every environment the planet offered. They lived in dense forests, open floodplains, coastal wetlands, highlands shaped by rising mountains, and even regions near the poles where forests grew under long summer days and long winter nights. Their forms reflected this diversity. Some were built like moving fortresses, wide and heavy, designed to process enormous amounts of plant material each day. Others were slender, quick, and alert, moving through the world with the focus of hunters that relied on speed, coordination, and sharp senses. Size alone set many of them apart from most modern animals. Some plant eaters grew longer than a city bus, their necks stretching out to reach leaves high in the canopy. Their tails extended behind them like living counterweights, balancing their massive bodies as they walked. To support such weight, their legs were thick and column-like, more like the pillars of a building than the limbs of a running animal. When they moved, the ground itself would have felt the vibration. Yet not all dinosaurs were giants. The same landscapes that supported towering herbivores also sheltered smaller forms, some no bigger than a dog or even a chicken. These animals often lived in the shadow of their larger relatives, moving quickly through undergrowth, feeding on insects, small animals, or plant matter. Their lighter bodies and sharper senses allowed them to survive in a world where danger could appear suddenly and from many directions. Plant-eating dinosaurs formed the foundation of many land-based ecosystems. They converted the energy stored in leaves, stems, and seeds into muscle, bone, and motion. In doing so, they made that energy available to the predators that hunted them. Different groups specialized in different types of vegetation. Some had broad, flat teeth suited for grinding tough plant material. Others had narrow beaks and shearing teeth designed to clip leaves or strip branches. The rise of flowering plants added new options to this menu. Fruits, seeds, and softer leaves became part of the available food in some regions. This may have influenced how certain herbivores fed, encouraging more selective browsing or seasonal movements to follow the growth and flowering cycles of plants. Large herds might move across the landscape, not just in search of water, but in response to the shifting availability of food. Herding itself was an important behaviour for many species. Moving in groups provided protection against predators, especially for young and vulnerable individuals. A single large animal might be an impressive sight, but a group of them moving together would have been impossible to ignore. The sound alone, the combined movement of dozens or hundreds of heavy bodies, would have carried across open ground and through forest corridors. Predatory dinosaurs in turn adapted to this reality. Some hunted alone, relying on stealth and sudden bursts of speed. Others may have worked in groups, coordinating their movements to isolate and bring down larger prey. Their bodies reflected their roles. Long legs, flexible spines, and strong tails allowed for quick turns and rapid acceleration. Sharp claws and teeth were tools for gripping, tearing, and holding on. Senses played a key role in these interactions. Eyes positioned toward the front of the head provided depth perception, useful for judging distance during a chase. Nostrils and internal structures associated with smell suggest that many predators could track prey by scent. Hearing too would have been important, allowing animals to detect movement or calls from far away. The landscapes they moved through were not empty backdrops. Forests created cover and obstacles. Open plains offered long sightlines but little shelter. River valleys and wetlands could slow movement and create natural bottlenecks. Each environment shaped how hunting and feeding played out, favouring different strategies and body types. Social behaviour added another layer of complexity. Fossil evidence, such as groups of individuals preserved together, or trackways showing multiple animals moving in the same direction, suggests that some dinosaurs lived and travelled in groups for much of their lives. Within these groups, there may have been structures based on age, size, or experience. Adults could provide protection for younger members, while juveniles might stay closer to the centre of the group. Reproduction was another critical part of this world. Dinosaurs laid eggs, often in nests built from vegetation, sediment, or scraped-out depressions in the ground. Some species appear to have returned to the same nesting sites year after year, creating colonies where many individuals laid their eggs in close proximity. This behaviour offered some protection through numbers, but it also attracted predators drawn by the concentration of food. Care for young varied. In some cases, adults may have stayed near nests, guarding them or even feeding hatchlings. In others, the young likely had to fend for themselves soon after emerging. The degree of care would have influenced survival rates and, over time, the evolution of behaviour and body form. Growth rates during the Cretaceous were often fast, especially in large species. Bone studies show patterns of rapid growth in early life, allowing young animals to reach sizes that made them less vulnerable to predators in a relatively short time. This strategy required a steady supply of food and energy, tying the success of these animals closely to the productivity of their environment. Seasonal changes still mattered, even in a generally warm world. Rainy and dry periods influenced plant growth and water availability. In some regions, herds may have moved with these cycles, following rivers during dry times or spreading out when vegetation was abundant. Predators would have tracked these movements, creating a shifting pattern of presence and absence across the landscape. Communication among dinosaurs likely involved more than just sight. Body posture, colour patterns, and possibly sounds would have played roles in signalling intentions, whether to attract a mate, warn off a rival, or coordinate movement within a group. Some species had elaborate crests, horns, or frills. These structures may have been used for display, making individuals more visible to others of their kind across open spaces. The sheer physical presence of large dinosaurs shaped the land in lasting ways. Their feeding habits could open up forests, breaking branches and knocking down smaller trees. Their movement compacted soil, creating trails and wallows. In wetlands, their weight could change the flow of water, deepening channels or creating new pools. Over time, these effects influenced where plants could grow and where smaller animals could live. Even their waste contributed to the system. Droppings returned nutrients to the soil, supporting plant growth and providing food for insects and microbes. This recycling of material kept energy and matter moving through the ecosystem. Not all dinosaurs fit neatly into the roles of hunter or grazer. Some species likely ate a mix of plant and animal matter, adapting their diets based on what was available. This flexibility could be an advantage in environments that changed with the seasons or over longer periods. The presence of dinosaurs also influenced other groups of animals. Mammals, mostly small during this time, often lived in burrows or stayed active at night, possibly to avoid larger daytime predators. Reptiles, amphibians, and birds filled niches around the edges of dinosaur-dominated spaces, finding ways to survive in a world shaped by much larger bodies. In coastal regions, dinosaurs moved between land and water, feeding on plants near shorelines or hunting small animals in tidal zones. Some footprints preserved in ancient sediment show tracks leading into shallow water, suggesting that these animals did not avoid wet environments. They were part of the boundary between land and sea, using the resources of both. Polar regions, surprisingly, also hosted dinosaurs. Fossils found at high latitudes show that some species lived in areas that experienced long periods of darkness each year. While temperatures were milder than today, these animals still had to cope with seasonal changes in light and plant growth. How they did so remains an area of active study, but possibilities include migration, changes in activity patterns, or reliance on stored energy. The variety of forms and behaviours during this time reflects a long period of success. Dinosaurs had been evolving and spreading for millions of years, and by the Cretaceous, they had filled many of the largest and most visible roles in land-based ecosystems. This was not a brief peak, but a sustained presence, supported by the warm climate, productive landscapes, and the ongoing reshaping of the continents. Yet even in this apparent stability, change was always present. New species appeared as others disappeared. Shifts in climate, sea level, and vegetation altered, which forms thrived in certain regions. Competition between species could drive the evolution of new traits, whether sharper teeth, stronger limbs, or more elaborate displays. The fossil record preserves hints of these transitions. In some layers of rock, one kind of dinosaur becomes more common as another fades away. In others, sudden changes suggest periods of environmental stress, perhaps caused by volcanic activity, shifts in ocean circulation, or changes in atmospheric composition. These patterns remind us that dominance in nature is rarely permanent. Even groups that seem firmly established are subject to the same forces of change as everything else. During the Cretaceous, dinosaurs were at the height of their diversity and spread, but the systems that supported them were still moving, still adjusting, still capable of producing surprises. The idea of a golden age can be comforting, suggesting a time of balance and success. In many ways, this period was exactly that for dinosaurs. They were numerous, varied, and deeply integrated into the landscapes of the planet. Their presence shaped the daily rhythm of life on land, from the growth of plants to the behaviour of smaller animals. If you imagine yourself in this world standing at the edge of a wide plain or in the shadow of a forest, you might feel the ground tremble as a herd passes nearby. You might see shapes moving in the distance, their outlines softened by heat and dust. The air would carry the sounds of movement, calls, and the constant background of insects and wind. At the same time, there would be quieter moments. Early morning light filtering through leaves, a still pond reflecting the sky, a small animal darting through undergrowth careful to stay hidden. The presence of giants does not erase the smaller, more subtle parts of the world. It simply adds another layer to them. As the day moves on, shadows lengthen and shorten, temperatures rise and fall, and the cycle continues. The land supports its inhabitants, and they in turn shape the land, in a relationship that feels steady and enduring when viewed from within. But if you step back and look at this age from the long perspective of deep time, you can see that even this long reign is part of a larger story. The forces that allowed dinosaurs to thrive are the same forces that will, eventually, change the conditions of their world. It is enough to sit with the image of a planet where large, complex animals move across warm, green landscapes, filling the space between ground and sky with their presence. The world feels full, active, and balanced in its own way. Beneath the towering bodies and sweeping tails that often draw the eye first, there was another layer of life moving just as carefully, just as purposefully, through the same warm landscapes. Survival in the Cretaceous was not only about size or strength. It was shaped by timing, awareness, and a long list of small decisions made every day by animals that needed to eat without being eaten. The world ran on a set of quiet agreements, unspoken but deeply felt, between those who hunted and those who tried to stay one step ahead. The rhythm of each day began before the sun climbed high. In the early light, when the air was cooler and shadows were long, many animals became active. For plant eaters, this was a good time to move and feed, before the heat of the day made every step more tiring. For hunters, it was a chance to use the low angle of the sun and the broken light of the forest to hide their approach. Herds were one of the most visible responses to danger. When animals gathered in groups, they created a living network of eyes, ears, and noses. One individual might miss the rustle of leaves or the faint scent of a predator on the wind, but in a group the chances of someone noticing increased. This shared awareness allowed herds to react quickly, bunching together, changing direction, or breaking into a run as a single moving mass. The shape of a herd mattered. Some species moved in loose formations, spread out enough to cover a wide area while feeding, but close enough to stay within sight of one another. Others travelled in tighter clusters, especially when young animals were present. In these groups, the smallest and most vulnerable members often stayed near the centre, shielded by larger bodies on all sides. Predators learned to read these patterns. A tightly packed herd could be difficult to penetrate, but a loose one might offer opportunities. An animal that strayed too far from the group, slowed by injury or age, became a potential target. The art of hunting often involved patience, watching for these small breaks in the structure of a herd rather than charging in without a plan. Speed played a role, but so did endurance. Some predators were built for short, explosive bursts, relying on surprise and power to close the distance quickly. Others were better suited to longer chases, using steady movement to tire their prey. The choice of strategy depended on the environment. Dense forests favoured ambush, with cover and limited lines of sight. Open plains offered room to run, but also made it harder to approach unnoticed. The senses were finely tuned tools in this exchange. Eyes adapted to detect movement against complex backgrounds. Nostrils picked up faint traces carried on the air. Ears caught the smallest sounds of a footstep or a snapping twig. Even vibrations through the ground could signal the approach of something large and heavy. For plant eaters, feeding itself was often a careful act. Lowering the head to crop leaves or reach into shrubs meant taking eyes off the surroundings. Many species developed habits to reduce this risk. Some fed in turns, with a few individuals keeping watch while others ate. Others chose feeding spots with good visibility or quick access to cover. The landscape offered both help and hazard. Riverbanks, for example, were rich in vegetation and water, but they also funneled movement into narrow spaces. A herd crossing a shallow river might be more vulnerable, slowed by water and uneven footing. Predators could take advantage of these moments, positioning themselves along the edges where escape routes were limited. Forests provided shade and concealment, but they also created blind spots. In dense growth, sounds and scents could bounce and swirl, making it harder to pinpoint where something was coming from. Both hunters and hunted had to move carefully, using memory of the terrain as much as immediate perception. Young animals faced a different set of challenges. They were smaller, less experienced, and often more curious. Staying close to adults increased their chances of survival, but curiosity could still draw them into risky situations. A sudden movement in the undergrowth or a strange shape near the edge of the group might tempt a young animal to wander, creating exactly the opening a predator was waiting for. Reproduction and survival were closely linked. Nesting seasons, for example, created predictable patterns in the landscape. Large numbers of eggs or hatchlings in one area could attract predators from far away. Some species responded by nesting in large colonies, relying on sheer numbers to overwhelm predators. Others chose hidden or hard-to-reach sites, trading accessibility for safety. Predators, in turn, learned these patterns. The time of year when young animals were most abundant could become a period of relative ease for hunters, allowing them to build strength and raise their own young. This seasonal pulse of vulnerability and abundance shaped movement and behaviour across wide regions. Not every interaction ended in a chase. Often, the presence of a predator alone was enough to change the behaviour of a herd. Animals might shift their grazing patterns, avoid certain areas, or alter their daily routines to reduce risk. This created what ecologists sometimes call a landscape of fear, where the threat of danger influences where and how animals live, even when no attack actually occurs. These invisible boundaries could shape the growth of plants as well. Areas that herbivores avoided might see more vegetation, while heavily grazed regions could remain open. In this way, predators indirectly influenced the shape of the landscape, not just through what they ate, but through how their presence changed the behaviour of others. Communication within and between species added another layer to this system. Alarm calls, body postures, and changes in movement could signal danger. A sudden lift of the head, a freeze in motion, or a sharp sound might ripple through a group in moments, turning calm feeding into coordinated escape. Some animals used deception as a survival tool. Blending into the background through coloration or patterning made it harder to be seen. Staying still could be just as effective as running, especially in environments where movement was more noticeable than shape. Predators also use camouflage, their bodies marked in ways that broke up their outline against shadows and foliage. Time of day mattered. Some species were more active in the early morning or late evening, taking advantage of lower light levels. Others preferred the heat of midday or the cool of night. By occupying different temporal niches, animals reduced direct competition and encounters, allowing more species to share the same space. Water sources were natural meeting points. In dry periods, animals of many kinds gathered around rivers, lakes, and wetlands. These places became hubs of activity, but also zones of heightened risk. The need to drink could override caution, drawing even the most careful animals into exposed positions. Social bonds within herds could influence survival in subtle ways. Individuals that stayed close to trusted companions might benefit from shared vigilance. Those on the edges of a group, whether by choice or circumstance, faced greater danger. Over time, these patterns could affect which animals lived long enough to reproduce, shaping the traits passed on to the next generation. Predators, too, sometimes formed social groups. Working together allowed them to tackle larger prey or control a wider area. Coordination required communication and learning, suggesting that intelligence and social awareness were valuable traits in this ongoing contest. Insects and smaller animals played their part as well. The presence of scavengers meant that little went to waste. After a hunt, smaller creatures moved in to feed on what was left behind, returning nutrients to the soil and water. This recycling kept energy flowing through the system, supporting new plant growth and, in turn, new herbivores. Disease and injury added another dimension to survival. A wound that might be survivable in a safe environment could become fatal in a world full of predators. Animals that limped, moved slowly, or showed signs of weakness stood out. At the same time, the ability to heal quickly or avoid injury in the first place became an important factor in long-term survival. Weather could tip the balance as well. Heavy rain might mask sounds and scents, making it harder for predators to track prey or harder for prey to hear a hunter's approach. Drought could concentrate animals around limited water sources, increasing encounters. Cold spells or heat waves, even in a generally warm climate, could stress populations and change behaviour. Learning and memory were quiet but powerful tools. Animals that remembered the locations of safe routes, dense cover, or reliable food sources had an advantage. Those that recognised the signs of danger, whether a particular scent or a shape in the distance, could react more quickly next time. Over long periods, these individual experiences accumulated into patterns of behaviour shared across generations. Young animals learned from watching adults. Successful strategies were repeated. Less effective ones faded away. This cultural transmission, though not recorded in fossils, would have been a real and influential part of life. The balance between hunters and herds was never fixed. Changes in plant growth, climate, or landscape could shift the advantage from one side to the other. A new river channel might create fresh grazing grounds, boosting herbivore numbers. A volcanic event or drought could reduce food, making prey more scarce and forcing predators to range farther. These shifts rippled through the system. An increase in herbivores might lead to more grazing pressure on plants, changing the composition of vegetation. A decline in predators could allow certain prey species to expand, altering the structure of herds and the dynamics of movement. Even the smallest changes could have large effects when they spread across wide areas and long times. The world of the Cretaceous was a web of connections, where survival depended not just on individual strength or speed, but on how each animal fit into the larger pattern of life. If you picture this web from above, it might look like a map of invisible lines, tracing the paths animals took each day, the places they avoided, the routes they followed to water and shelter. These lines shifted with the seasons, with the weather, and with the slow movement of the land itself. In quieter moments, When no chase was underway and no alarm was raised, the system still worked in the background. A herd grazed. A predator rested in the shade. Insects moved between flowers. Birds watched from branches. Energy flowed from plant to animal to animal, and back into the soil. The absence of immediate drama did not mean the absence of tension. Every movement carried the possibility of change. A sudden noise, a shift in the wind, a shadow moving across the ground could transform calm into motion. As this steady exchange continued day after day, it shaped not just individual lives, but entire species. Traits that improve survival in this complex, shifting world became more common. Over time, these changes produced the diversity of forms and behaviours that filled the Cretaceous landscapes. The quiet rules of survival were not written down, but they were learned, tested, and reinforced with every successful escape and every failed hunt. They were part of the invisible structure that held the living world together. Letting this sense of ongoing balance settle, you can begin to feel how life in this age was not only about dominance or conflict, but about adjustment and response. Every animal, whether hunter or herd member, was part of a larger conversation with its environment. Below the wide shifting line where land met sea, a different world unfolded, one that followed its own rhythms and carried its own giants through quiet, sunlit depths. While forests rustled and herds moved across open ground, the oceans of the Cretaceous held vast spaces of warm water, layered with life from the surface down to the darker reaches below. These waters were not empty expanses between continents. They were living systems, filled with motion, sound, and slow, powerful bodies that shaped the flow of energy just as surely as the largest animals on land. The surface of these ancient seas often looked calm, broken only by waves, drifting debris, or the occasional ripple of something moving just beneath. Yet below that thin boundary of air and water, the scene changed quickly. Sunlight streamed down in shifting beams, illuminating clouds of microscopic life that floated near the top. These tiny organisms, plankton, were the foundation of everything that followed. They captured sunlight and turned it into energy, forming the first link in long chains that reached up to the largest predators in the sea. Plankton came in many forms. Some were plant-like, using photosynthesis to grow. Others were small animals feeding on the plant plankton or on each other. Together they formed drifting communities that moved with currents and tides. Where conditions were right, these communities grew dense, colouring the water with faint green or blue hues and supporting enormous numbers of larger creatures. Fish moved through this upper layer in schools that could stretch for long distances. Their bodies reflected the light in quick flashes as they turned and twisted together, responding to changes in current or the approach of a predator. Some species were small and quick, feeding on plankton or tiny invertebrates. Others grew larger, hunting smaller fish and carving their own paths through the water. Among these fish swam animals that were not fish at all, but reptiles that had returned to the sea millions of years earlier. By the Cretaceous, these marine reptiles had diversified into a range of forms, each adapted to a different way of living in the water. Their bodies were shaped by the need to move efficiently through a dense, resistant medium, and their designs reflected a long history of trial and adjustment. One group, the mosasaurs, were among the most striking. They were large, powerful predators, with long bodies, strong tails, and jaws lined with sharp teeth. Some grew as long as a school bus, their presence enough to scatter fish and smaller animals long before they came into view. Their tails ended in broad flukes that provided strong propulsion, allowing them to surge forward in sudden bursts when they closed in on prey. These reptiles likely hunted a wide range of animals. Fish, squid-like creatures, and even other marine reptiles were all potential targets. Their flexible jaws allowed them to swallow large prey, and their strong muscles gave them the ability to overpower animals that might otherwise have been dangerous to approach. Another group, the plesiosaurs, moved through the water in a very different way. Some had long necks and small heads, giving them a silhouette that looked almost like a floating log with a narrow extended reach. Their 4 large paddle-like limbs beat through the water in a coordinated motion, more like the flight of a bird than the swimming of a fish. This style of movement allowed them to maneuver with precision, gliding through reefs, shallow seas, and open water alike. Short-necked relatives, often called pliosaurs, took on a more aggressive form. With large heads and powerful jaws, they were built for speed and strength, capable of chasing down and capturing sizable prey. Their presence added another layer of pressure to the marine food web, shaping the behaviour and distribution of other animals in the sea. Sharks were also an important part of this world. Though different from many modern species, they already showed the key features that make sharks effective hunters today. Streamlined bodies, keen senses, and rows of replaceable teeth allowed them to feed on a wide range of animals. Some species were small and specialised, while others grew large enough to challenge almost anything they encountered. Cephalopods, a group that includes modern squid and octopus, filled many roles in these oceans. Some had long coiled shells, drifting or swimming slowly, using jets of water to move. Others lacked external shells, making them more flexible and agile. Their intelligence and ability to change colour and shape likely helped them avoid predators and capture prey. The seafloor itself supported a different community. In shallow areas, where sunlight could still reach, reefs formed from the skeletons of small organisms and the growth of algae and corals. These reefs created complex structures of ridges, holes, and overhangs, offering shelter to countless small animals. Crustaceans, mollusks, and small fish lived in these spaces, feeding on algae, detritus, and each other. Farther down, where light faded, life took on different forms. Here, the energy from the surface arrived as falling particles of dead plankton and waste, a slow rain of organic material that fed creatures living in the darker layers. Worms, small crustaceans, and other invertebrates processed this material, breaking it down and returning nutrients to the system. Currents moved through all these layers, connecting distant places. Warm water carried life from one region to another, while cooler currents returned toward the equator. These movements influenced where plankton bloomed, where fish gathered, and where large predators hunted. A change in current patterns could shift entire ecosystems, altering which species thrived in a given area. Sea level during much of the Cretaceous was high, creating broad, shallow seas over continental shelves and inland regions. These areas were especially productive. Sunlight, nutrients from land, and warm temperatures combined to support dense growth of plankton and plants. As a result, these shallow seas became nurseries for many species, providing food and shelter for young fish and invertebrates. The inland sea that once split North America is a good example. It connected polar waters to tropical ones, allowing species to move along a long, continuous corridor. Fossils from this region show a mix of animals from different environments, suggesting a rich and varied ecosystem shaped by the meeting of different currents and climates. Storms played a role in this underwater world as well. Strong winds and waves mixed the upper layers of the ocean, bringing nutrients from deeper water up to the surface. This mixing could trigger bursts of plankton growth, which in turn attracted fish and larger predators. After a storm, the sea might appear calmer on the surface, but below, a wave of activity would move through the food web. The chemistry of the water mattered deeply. Levels of oxygen, salt, and nutrients influenced which species could survive in different regions. In some areas, especially in deeper or more enclosed basins, oxygen levels could drop, creating zones where few animals could live. These low oxygen regions shaped migration patterns, pushing mobile species toward more hospitable waters. Temperature differences created layers in the water, with warmer, lighter water resting on top of cooler, denser layers. This stratification could limit mixing, affecting how nutrients and oxygen move between depths. Changes in climate or current patterns could break down these layers, altering conditions throughout the water column. Life in the oceans was not only about predation and escape. Many animals formed partnerships. Some fish cleaned parasites from larger creatures, gaining protection and food in return. Others lived among the tentacles of stinging animals or within the structures of reefs, using these environments as safe havens. Reproduction took many forms. Some species released eggs and sperm directly into the water, relying on currents to bring them together. Others laid eggs in protected areas on the seafloor or attached them to plants and rocks. A few marine reptiles may have given birth to live young, avoiding the need to return to land. The young that emerged into this world faced immediate challenges. Tiny larvae and hatchlings drifted in the plankton, vulnerable to anything that could swallow them. Survival depended on numbers, with many more produced than could ever reach adulthood. This constant turnover fed the rest of the ecosystem, ensuring that energy continued to flow upward through the food web. Sound travelled differently in water than in air, and many marine animals likely used this to their advantage. Vibrations could carry over long distances, allowing animals to sense movement or communicate without relying on sight. The ocean, though often imagined as silent, was probably filled with a range of low rumbles, clicks and pulses created by moving bodies and shifting currents. Light too behaved in unique ways. As depth increased, colours faded, leaving the world in shades of blue and grey. Some animals developed reflective surfaces or patterns that helped them blend into this dim environment. Others may have used bioluminescence, producing light to attract prey or confuse predators, though direct evidence from the Cretaceous is limited. The edges of the ocean, where water met land, were among the most dynamic places of all. Tides exposed and covered wide areas each day, creating zones that were sometimes wet, sometimes dry. Animals living here had to tolerate changes in temperature, salinity, and oxygen levels. Those that could handle this variability often found rich feeding grounds. Rivers delivered fresh water, sediment, and nutrients into these coastal zones. Plumes of murky water spread out into the sea, creating gradients of salt and clarity. Some species thrived in these mixed conditions, using them as corridors to move between freshwater and marine environments. Over long periods, the remains of marine life built up on the seafloor. Shells, bones, and microscopic skeletons formed thick layers of sediment. These layers recorded changes in climate, chemistry, and biology, preserving a history of the ocean in stone. Chalk cliffs, limestone beds, and fossil-rich shales are the quiet remnants of these ancient seas. The influence of the oceans extended far beyond their boundaries. By absorbing and releasing heat, they helped regulate the climate of the entire planet. By taking in carbon dioxide, they played a role in controlling the composition of the atmosphere. The life they supported produced oxygen and locked away carbon, shaping the air that land animals breathed. The movement of water also connected distant parts of the world. Species could spread along currents, reaching new coastlines and shallow seas. This mixing of life contributed to the global character of many marine groups, with similar forms appearing on continents that were far apart on the surface. Even the deep ocean, largely hidden from view, was part of this system. Though less productive than shallow waters, it covered a vast area. The slow rain of organic material from above supported a community of animals adapted to low light and limited food. These creatures in turn processed material that might otherwise have been lost, keeping nutrients in circulation. The presence of large predators shaped behaviour throughout the sea. Schools of fish moved in tight formations, changing direction in near-perfect unison when threatened. Smaller animals stayed close to cover, whether that was a reef, a patch of vegetation, or a cloud of plankton that could hide their outlines. The balance between risk and reward was constant. Feeding in open water offered access to rich food sources, but also exposure. Staying near the seafloor or within reefs provided shelter, but often meant competing with many others for limited resources. Each species found its own place along this spectrum. Seasonal changes affected the ocean as well. Shifts in wind and sunlight influenced currents and surface temperatures, leading to cycles of productivity. In some regions, certain times of year would see an abundance of plankton and fish, drawing predators from far away. At other times, the same areas might be relatively quiet. Long-term changes, driven by the slow movement of continents and the opening and closing of seaways, altered these patterns on much larger scales. A new passage between oceans could bring in different species, change current directions, and transform local ecosystems. The picture that emerges is not one of a simple, uniform ocean, but of a layered, connected world, full of pathways and boundaries. Life moved through this world in 3 dimensions, up and down, near and far, following currents, chasing food and avoiding danger. If you imagine drifting just below the surface, letting the water carry you gently along, you might see shapes passing in the distance, shadows moving through the blue. Above, light would ripple across the water, broken by waves and clouds. Below, darker forms would fade into the depths, hinting at spaces not yet explored. The ocean during the Cretaceous was not a backdrop to the story of life on land. It was an equally important stage, hosting its own dramas, successes, and quiet moments of balance. The energy captured by plankton at the surface travelled through fish, reptiles, and countless smaller creatures, linking the sun to the deepest parts of the sea. As this underwater world continues to unfold in your thoughts, it becomes easier to see how closely it was tied to everything above it. Rivers, rain, and erosion carried material from land to sea. Winds and currents carried moisture and heat back toward the continents. Life moved between these realms, sometimes directly, sometimes through long chains of connection. From the stillness of deeper water to the busy surface layers, the oceans held a mirror to the complexity of the land. Both were shaped by the same forces of climate, geology, and time. Tucked away beneath the sweeping branches of forests and the heavy footsteps of much larger neighbours, another story unfolded quietly, one that rarely announced itself with sound or size. In the warm, shifting landscapes of the Cretaceous, early mammals lived lives defined not by dominance but by subtlety, patience, and an ability to make the most of small spaces and brief moments of safety. While giants shaped the visible outline of the world, these tiny survivors worked within the spaces left behind, turning shadows, burrows, and nightfall into their greatest allies. Most mammals of this time were small, often no larger than a modern mouse, rat, or squirrel. Their bodies were built for efficiency rather than display. Short legs kept them close to the ground. Flexible spines allowed them to twist and turn quickly. Fur, already a defining feature, helped regulate body temperature, keeping them warm during cooler nights and in shaded forest floors where sunlight barely reached. This covering also dulled sound and softened outlines, making them harder to notice in a world where being seen could mean being eaten. The ground itself was their primary stage. Leaf litter, fallen branches, and uneven soil created a complex terrain filled with hiding places. Beneath this surface, networks of burrows and natural cavities offered shelter from predators, heat, and sudden changes in weather. Some mammals dug their own tunnels, pushing soil aside with strong forelimbs and reinforced claws. Others took advantage of spaces left behind by roots, rocks, or the activity of other animals. Night brought opportunity. As larger, visually oriented predators settled into rest, the darkness gave small mammals a layer of protection. Their senses were tuned for this low-light world. Large eyes gathered what little light was available. Sensitive whiskers brushed against nearby objects, mapping the environment through touch. Ears caught faint sounds, allowing them to detect danger or the movement of potential prey. Food for these animals came in many forms. Insects were an important part of their diet, especially in environments rich with flowering plants that supported large populations of bugs. Beetles, larvae, and other small invertebrates provided protein and energy. Seeds and fruits, increasingly common as flowering plants spread, offered another source of nourishment. Some mammals likely ate a mix of both, adjusting their diet based on what was available in a given season or place. This flexibility was one of their greatest strengths. Where larger animals depended on large quantities of a specific type of food, small mammals could survive on a wider range of resources. A patch of insects near a rotting log, a cluster of seeds dropped by a passing herbivore, or the remains of a larger animal's meal could all become part of their daily intake. Teeth tell much of this story. Fossils show that early mammals had a variety of tooth shapes, each suited to different kinds of food. Sharp cusps for piercing and cutting insects, broader surfaces for grinding plant material. This diversity allowed them to fill many small ecological roles, often in the same area, without directly competing with one another. Reproduction followed a different rhythm than that of the large animals around them. Smaller bodies generally meant shorter lifespans and faster reproductive cycles. Some mammals likely produced several litters over the course of a year, increasing the chances that at least some of their young would survive in a dangerous environment. This strategy balanced the high risks they faced from predators, weather, and disease. Care for young was an important part of their lives. Unlike reptiles, mammals gave birth to live young, or, in some early groups, laid eggs that hatched into very dependent offspring. In both cases, the young required protection and nourishment. Mothers provided milk, a rich source of energy that allowed babies to grow quickly and develop in the safety of a burrow or nest. This period of care created strong bonds between parent and offspring. It also tied families to specific locations for a time, making the choice of a safe nesting site critical. A well-hidden burrow could mean the difference between a successful litter and a loss to a passing predator. Movement across the landscape was cautious and deliberate. Small mammals often travelled along established paths under cover, using fallen logs, dense vegetation, and rock outcrops to stay hidden. Open ground, especially in daylight, was risky. Crossing it required speed and careful timing, often in short, darting runs from one piece of cover to the next. The presence of large dinosaurs influenced these patterns in subtle ways. The trails created by heavy feet could become pathways for smaller animals, offering compacted ground that was easier to move across. At the same time, these trails were also places where predators might look for activity, adding another layer of risk. Scavenging played a role as well. The remains of large animals, whether left behind by predators or after natural death, became temporary centres of activity. Insects arrived first, drawn by the smell. Small mammals followed, feeding on both the insects and any accessible scraps of flesh. These events provided bursts of food, but they also attracted attention, turning a potential feast into a dangerous gathering. Scent marked much of this hidden world. Mammals use smell to find food, recognize one another, and define territories. Scent trails could guide individuals back to a nest or lead them toward a potential mate. At the same time, these same trails could be followed by predators, so leaving too strong a signal carried its own risks. Communication was often quiet and close range. Soft calls, squeaks, and body language helped coordinate movement between individuals without drawing unwanted attention. Touch, through grooming or simple contact, reinforced social bonds and helped maintain group cohesion in species that lived together. Not all mammals lived alone. Some likely formed small groups or family units, sharing nests or burrows. Living together offered warmth and protection, but it also meant competition for food and space. Balancing these costs and benefits shaped how different species organised their social lives. Water sources were important, but approached carefully. Streams and pools offered drinking water and insects, but they were also gathering points for many animals, including predators. Small mammals often visited these places at quiet times, using cover along the banks to stay hidden while they drank. The changing seasons of the Cretaceous, though milder than those of many modern regions, still influenced their lives. Periods of heavy rain could flood burrows, forcing animals to relocate. Drier times might reduce insect populations, pushing mammals to rely more on seeds or stored food. Some species may have cached food in their burrows, creating small reserves for leaner periods. The spread of flowering plants opened new possibilities. Fruits and seeds could be carried away and stored, allowing mammals to move plant material across the landscape. In doing so, they became unintentional partners in the spread of vegetation, helping plants colonize new areas. This quiet collaboration between small animals and plants contributed to the changing face of the land. Predators of these mammals were not limited to dinosaurs. Birds, reptiles, and even other mammals hunted them. Snakes in particular were well suited to slipping into burrows and tight spaces. This constant pressure reinforced the need for vigilance and adaptability. Learning and memory played a role here as well, knowing which areas offered the best cover, which paths were safest, and which times of day were least risky could improve survival. Young animals learned these patterns by following adults, building a mental map of their surroundings over time. The variety of environments created by shifting continents and climates allowed different mammal species to specialize. Some favored forest floors rich in insects and leaf litter. Others thrived in open areas where seeds were abundant. Wetlands supported species that fed on aquatic insects and small invertebrates. This specialization reduced direct competition and allowed more species to coexist in the same region. Though small, these animals were not insignificant. They were part of the same web of energy that connected plants, insects, and larger predators. By eating insects, they helped control populations that might otherwise grow too large. By spreading seeds, they influenced the growth of vegetation. By serving as prey, they supported birds, reptiles, and small predators. Their presence added resilience to the ecosystem. Because they reproduced quickly and adapted easily, they could recover from local disruptions more rapidly than many larger animals. A flood, fire, or volcanic event might wipe out populations in one area, but nearby groups could move in and repopulate the space over time. In the fossil record, these mammals often appear as small, delicate bones and teeth, easy to overlook among the massive skeletons of dinosaurs. Yet these fragments tell a story of persistence. They show lineages that continued through changing conditions, surviving alongside giants for millions of years. Some of the traits that define modern mammals were already well established. Warm-blooded metabolism allowed for activity in cooler conditions and at night. Differentiated teeth supported varied diets. Hair provided insulation and sensory input. Parental care increased the survival of young. These features did not guarantee dominance in the Cretaceous world, but they laid the groundwork for what would come later. The ability to adapt quickly, to use small spaces, and to exploit a wide range of resources would become crucial in times of change. If you imagine crouching down to the level of these animals, the world would look very different. The towering trunks of trees would become distant columns. The ground would be a landscape of hills and valleys formed by roots, stones, and fallen leaves. Every step would reveal new scents, new sounds, and new possibilities. From this low vantage point, the presence of large dinosaurs would be felt more than seen. Vibrations through the soil, shifting shadows, and distant noises would signal their movement. These cues would guide when to hide, when to move, and when to stay still. The hidden world of early mammals was a world of constant attention. It was shaped by quick decisions, brief opportunities, and the need to balance risk and reward in every action. Yet within this careful, constrained life, there was also room for exploration, play among young animals, and the quiet routines of feeding, grooming, and resting. Over long stretches of time, these small lives added up. Generation after generation, mammals persisted, changed, and diversified. They filled niches that were too small, too dark, or too unpredictable for larger animals to use. This persistence meant that when conditions eventually shifted in dramatic ways, mammals would be ready to respond. Their story during the Cretaceous is not one of quiet insignificance, but of preparation. building a set of tools and behaviours that would later allow them to step into much larger roles. It becomes easier to notice how even the smallest creatures were part of the planet's broader processes. Their burrows affected soil structure, their feeding influenced plant growth, their movements connected different parts of the landscape. Deep within the planet, far below roots, rivers, and the quiet pathways of small animals, there was another world in constant motion, one defined not by leaves or water or air, but by heat, pressure, and the slow, restless movement of molten rock. The surface of the Cretaceous Earth, with all its forests, seas, and living creatures, rested on a foundation that never truly stood still. It floated, in a sense, on a layer of material that could bend, flow, and rise, carrying with it the energy stored since the planet first took shape. This inner activity expressed itself most clearly through volcanoes, though even that word can suggest something more sudden and dramatic than what often happened. While some eruptions were explosive and brief, many of the most important volcanic events of this time unfolded slowly, over thousands or even millions of years. Instead of a single mountain bursting into life, vast cracks in the crust opened and allowed lava to pour out in long glowing rivers that spread across the land and cooled into broad dark plateaus. These events did not always draw attention in the way a towering volcano might. From the perspective of an animal living nearby, the change could feel gradual. A landscape that once held trees and rivers might, over many generations, become covered in layer after layer of solidified rock. New surfaces formed where old ones had been, altering how water flowed, how plants took root, and how animals moved through the area. The source of all this activity lay in the mantle, the thick layer of hot, semi-solid rock beneath the crust. Heat from the planet's core rose through this layer in slow currents, like a vast invisible circulation system. Where these currents pushed upward, the crust above them could thin, crack, or rise. Where they sank, the crust might be pulled downward, creating basins or deepening ocean floors. During the Cretaceous, some of these upward currents, known as mantle plumes, were especially powerful. When a plume reached the base of the crust, it could create enormous amounts of magma. This magma, finding pathways to the surface, produced what geologists now call large igneous provinces. These are regions where lava flows covered hundreds of thousands, or even millions of square kilometers, reshaping entire parts of continents. One of the most well-known of these regions formed in what is now India. Over time, massive lava flows built up thick layers of rock, creating what are called the Deccan Traps. The word traps comes from a term for steps, reflecting the way erosion later carved these layers into a series of terraces. During their formation, however, these flows would have been vast, glowing fields of molten stone, slowly advancing across the land. The release of lava was only part of the story. Volcanoes also released gases, and these gases had far-reaching effects. Carbon dioxide, sulfur dioxide, and water vapour entered the atmosphere in large quantities. Carbon dioxide contributed to warming by trapping heat, while sulfur dioxide could form tiny particles that reflected sunlight, sometimes leading to temporary cooling. The balance between these effects depended on how much of each gas was released and how long the activity continued. Over long periods, repeated volcanic events could shift the climate in noticeable ways. An increase in carbon dioxide could push global temperatures higher, expanding warm conditions into regions that were previously cooler. This could change where plants grew, which animals thrived, and how oceans circulated. In contrast, a period dominated by sulfur-rich eruptions might create a haze in the atmosphere, reducing the amount of sunlight reaching the surface and briefly cooling the planet. These changes were not uniform or immediate. The atmosphere and oceans acted as buffers, absorbing and redistributing energy over time. Still, the breath of the planet in the form of volcanic gases was a constant presence in the background of the Cretaceous world, quietly influencing conditions across the globe. Volcanoes also shaped the chemistry of the land and sea. Ash, carried by the wind, settled over wide areas. This ash, once broken down by rain and weathering, released minerals into the soil. In many cases, this created fertile ground where plants could grow more easily. Entire ecosystems could develop on these enriched soils, turning what might seem like a destructive event into the foundation for new life. In the oceans, volcanic material entered through rivers and underwater eruptions. This added nutrients like iron and phosphorus to the water, which could stimulate the growth of plankton. Plankton blooms increased the base of the marine food web, supporting more fish and larger predators. At the same time, too much nutrient input could lead to low oxygen conditions in some areas, as the decomposition of large amounts of organic material used up available oxygen. These low oxygen zones shaped where marine life could survive, creating invisible boundaries beneath the surface. Underwater volcanoes, often hidden along mid-ocean ridges and seamounts, played a special role. Here, new crust formed as magma rose and cooled, pushing older seafloor away on either side. Hot, mineral-rich water flowed out of cracks in the rock, creating hydrothermal vents. Around these vents, unique communities of organisms thrived, using chemical energy rather than sunlight as the base of their food web. While we have limited direct evidence of such systems in the Cretaceous, the same processes that operate today were active then, suggesting similar hidden ecosystems existed in the depths. On land, volcanic landscapes created contrasts. Fresh lava flows were often barren at first, their surfaces hard and sharp, offering little for plants to take hold. Over time, however, cracks formed, dust settled, and small organisms moved in. Lichens and simple plants began the slow process of breaking down rock into soil. Seeds carried by wind or animals found places to sprout. Gradually, what had been a dark, empty surface turned green again. This cycle of destruction and renewal added to the patchwork nature of the Cretaceous world. Some regions were stable and unchanged for long periods. Others were in various stages of recovery from volcanic events. Animals moving across the landscape would have encountered a mix of old forests, young growth, open rock, and fertile plains, each offering different opportunities and challenges. The shape of the land was influenced by volcanic activity in more subtle ways as well. Large accumulations of lava added weight to the crust, causing it to sink slightly. This subsidence could create basins that later filled with water, forming lakes or shallow seas. In coastal areas, the interaction between rising or sinking land and sea level determined where shorelines formed and how they moved over time. Rivers responded to these changes by altering their courses. A lava flow might block a valley, forcing water to find a new path. Over time, the river would carve through or around the obstruction, leaving behind a record of its shifting route in layers of sediment. These records, preserved in rock, offer clues about the timing and scale of volcanic events. The influence of volcanoes extended into the air itself. Large eruptions could inject ash and gases high into the atmosphere, sometimes reaching the stratosphere. There, particles could spread around the globe, affecting climate far from the source. Sunsets might have appeared more vivid, with light scattering off fine ash in the air. The sky, though still blue, could take on subtle changes in colour and brightness during periods of intense activity. For living creatures, these atmospheric changes could be felt in simple physical ways. Reduced sunlight might slow plant growth. Cooler temperatures could alter animal behaviour. Heavy ashfall could cover leaves, making it harder for plants to photosynthesize and for animals to find food. In extreme cases, local populations might decline or move away, creating shifts in the distribution of species. Yet these disruptions were often temporary on the scale of geological time. The planet's systems tended to move back toward balance, guided by processes that absorbed carbon, broke down rock, and redistributed heat. Plants grew, soils formed, and life returned to areas that had been changed. The deep connection between volcanic activity and the carbon cycle is especially important. When volcanoes released carbon dioxide, it entered the atmosphere and oceans. Plants on land absorbed it through photosynthesis, incorporating carbon into their tissues. When these plants died, some of that carbon was returned to the air through decay, while some was buried in soil or sediment. Over long periods, this buried carbon could become part of the rock record, locked away until future geological processes released it again. In the oceans, plankton played a similar role. They took in carbon dioxide to build their bodies. When they died, their remains sank, carrying carbon to the seafloor. There, it could be buried under layers of sediment, forming limestone and other rocks. This slow movement of carbon between air, water, living things, and stone acted as a regulator for the planet's climate. Volcanoes, in this context, were both sources and participants in this cycle. They added carbon back into the system, keeping the long-term balance moving. Without this input, the planet might gradually lose carbon to burial, potentially cooling over very long timescales. The idea of the planet breathing can be a useful way to picture this. Not in a literal sense, of course, but as a pattern of exchange. Gases moved out of the Earth through volcanic vents and cracks. They were taken up by oceans and living things. They were returned through decay, weathering, and eventually more volcanic activity. This cycle unfolded over millions of years, shaping the conditions for life on the surface. The sound of this process would not have been a steady roar. Most of the time it would have been silent. Heat moved through rock without noise. Gases seeped out slowly in many places. Only during active eruptions would the planet's inner workings announce themselves more clearly, with rumbling ground, glowing lava, and clouds rising into the sky. Animals living near these regions would have had to respond to these events. Some might flee when the ground shook or the air filled with ash. Others might be trapped by sudden changes in the landscape. Over time, populations in volcanic regions would adapt to these risks, favouring traits that allowed for quick movement or flexible behaviour. Plants too responded in their own ways. Some species were better at colonising fresh, mineral-rich soils. Their seeds could sprout in thin layers of ash, giving them an advantage in newly formed landscapes. These pioneer plants often prepared the ground for others, adding organic matter and creating shade that allowed more delicate species to follow. The presence of volcanic mountains and plateaus also influenced weather. High ground forced air upward, causing it to cool and release moisture as rain or snow. This created wetter conditions on one side of a range and drier conditions on the other, shaping the distribution of forests, wetlands, and open areas. In coastal regions, underwater eruptions and the creation of new seafloor altered the shape of the ocean basins. This could change how currents flowed, which in turn influenced climate and marine ecosystems far away. A shift in current direction might bring warmer water to a region that had been cooler, or vice versa, triggering changes in plankton growth and the species that depended on it. Even the magnetic field of the planet, generated by movement in the core, left its mark on volcanic rocks. As lava cooled, magnetic minerals within it aligned with the current direction of the field, recording a snapshot of that moment in time. These records now help scientists reconstruct the history of plate movement and volcanic activity. The Cretaceous, then, was not just shaped by what happened on the surface. It was deeply connected to processes far below, processes that moved slowly and relentlessly, influencing climate, chemistry, and the very shape of the world. If you imagine standing on a quiet plain, with no sign of a volcano in sight, it might be hard to believe that beneath your feet, rock was slowly flowing, heat was rising, and gases were moving toward the surface. The calm of the landscape would hide a deeper, ongoing activity that would continue whether or not any living thing noticed. This hidden motion reminds us that the planet is not a static stage. It is an active participant, shaping and reshaping the conditions for life over and over again. Forests grow, seas rise and fall, animals move and adapt, all in response to forces that begin far below the surface. The warmth of the climate, the shape of the continents, the spread of plants, and the patterns of life in the oceans and on land all trace back, in part, to the slow release of energy from within the Earth. High above the forests, plains, and shallow seas, there was a layer of the Cretaceous world that no animal could touch, yet every living thing depended on it. The sky was not just an empty space where clouds drifted and sunlight passed through. It was a moving system carrying heat, moisture, and invisible gases around the planet, shaping when rains fell, how warm days became, and which regions stayed green or turned dry. The atmosphere was a quiet guide, setting the rhythm for life below in ways that were felt more than seen. Air in this time carried a different balance of ingredients than it does today. Carbon dioxide levels were higher, and this extra presence influenced how much warmth the planet held on to. Sunlight entered through the upper layers of the atmosphere, warmed the surface, and then tried to escape back into space as heat. The carbon dioxide acted like a partial barrier, keeping some of that heat close to the ground. This created a generally warmer world, but not one without variation. Oxygen, the gas most animals rely on to breathe, was present in amounts that may have been similar to, or slightly higher than modern levels. This supported the high energy demands of active animals, including flying creatures and fast-moving predators. Plants, through photosynthesis, continually refresh this oxygen supply, linking the composition of the air directly to the growth of forests, fields, and plankton in the oceans. Water vapour played an equally important role. Warm air holds more moisture, and the Cretaceous atmosphere often carried large amounts of it. This moisture travelled with wind patterns, rising and falling as temperatures changed. When warm, wet air cooled, it released rain. When it warmed again, it could carry more water upward, creating a constant cycle of movement between surface and sky. Clouds formed where this moisture gathered. Some were thin and high, spreading like pale veils across the sky and reflecting a portion of sunlight back into space. Others were thick and low, heavy with rain. These clouds influenced how much energy reached the surface and how much heat was trapped below, adding another layer of complexity to the planet's temperature balance. The movement of air around the globe followed broad circular patterns driven by the sun's uneven heating of the surface. Regions near the equator received more direct sunlight, warming the air there and causing it to rise. As it rose, it cooled and spread toward higher latitudes, eventually sinking again in cooler regions. This created large-scale circulation cells that carried heat and moisture across vast distances. The shape and position of the continents altered these patterns. Large land masses heated and cooled more quickly than oceans, creating pressure differences that influenced wind direction and strength. Mountains forced air to rise, cooling it and triggering rain on one side while leaving the other side drier. Open seaways allowed air and moisture to move freely between regions, linking distant climates together. Seasonal changes were guided by the tilt of the planet and its path around the sun, just as they are today. Different parts of the world experienced variations in daylight and temperature throughout the year. However, the overall warmth of the Cretaceous meant that these changes often felt softer than in many modern regions. In areas near the equator, seasons were less about temperature and more about rainfall. Periods of heavy rain alternated with drier stretches, shaping when plants grew most vigorously and when animals moved in search of water and food. Rivers swelled during wet times, spreading nutrient-rich sediment across floodplains. During drier periods, these same rivers might shrink, leaving behind isolated pools and damp ground where life clustered. Farther from the equator, variations in sunlight created more noticeable differences between times of year. Long summer days supported extended periods of plant growth, especially in high-latitude forests, where sunlight could last for many hours. Winters brought shorter days and cooler temperatures, but in many places these seasons were still mild compared to modern cold regions. The poles themselves were not locked in ice. Instead, they experienced long cycles of light and darkness, with months of continuous daylight followed by months of dim conditions. Plants and animals in these regions adapted to this pattern. Trees grew during the bright months, storing energy in their tissues to survive the darker times. Animals may have adjusted their activity patterns or relied on stored food and fat to get through periods when resources were less abundant. Storm systems were a natural part of this atmospheric dance. Warm, moist air rising from oceans could fuel large, long-lasting storms. These systems carried rain far inland, sometimes over wide areas, shaping landscapes through erosion and deposition. Strong winds accompanying storms could knock down trees, open gaps in forests, and spread seeds and spores across great distances. Lightning, produced by the buildup of electrical charges in storm clouds, added another element. It could ignite fires in dry regions, clearing vegetation and creating open spaces where new plants could grow. These fires were part of the natural cycle in some ecosystems, encouraging a mix of plant species and preventing any single type from dominating completely. The air also carried particles released by volcanoes. Ash and sulfur-rich aerosols could rise high into the atmosphere, spreading around the planet. For a time, these particles might reflect sunlight, slightly cooling the surface. Skies during these periods could appear hazy, with sunsets and sunrises showing deeper colours as light scattered through the fine dust. Over longer spans, the balance between these volcanic inputs and the absorption of carbon dioxide by plants and oceans influenced the overall climate. When more carbon entered the atmosphere than was removed, temperatures tended to rise. When removal outpaced release, cooling could follow. These shifts happened slowly, over thousands or millions of years, but their effects shaped the distribution of life. Air quality varied from place to place. Near active volcanic regions, the atmosphere might carry strong scents of sulfur and other gases. In dense forests, the air could be heavy with the smell of leaves, flowers, and decaying plant matter. Coastal areas mixed the scent of salt and moisture into the breeze. These sensory details, though fleeting, were part of how animals experienced their environment. Wind was another constant presence. Gentle breezes moved pollen between plants, helping conifers and flowering species reproduce. Stronger winds shaped the growth of trees, bending them and influencing the direction of their branches. In open areas, wind sculpted dunes and carried fine particles of dust across the land, adding minerals to soils far from their source. Insects and small animals were especially sensitive to these atmospheric conditions. Changes in temperature and humidity influenced when they were active, when they reproduced, and where they could survive. Because so many other species depended on insects for food, these shifts rippled outward, affecting birds, small mammals, and even large predators. Birds and flying reptiles experienced the sky in a more direct way. Air density, temperature, and wind patterns influenced how easily they could stay aloft and how far they could travel. Warm, rising air could create updrafts that allowed gliding creatures to soar with little effort. Strong winds could carry them over long distances, sometimes to entirely new regions. The upper layers of the atmosphere played a protective role as well. The ozone layer, formed by interactions between oxygen and sunlight, absorbed much of the sun's harmful ultraviolet radiation. This shield helped protect living tissues on the surface, especially in a world with high levels of sunlight reaching warm, exposed landscapes. Rain, when it fell, was rarely uniform. Some regions experienced frequent steady precipitation that kept soils moist and rivers flowing year-round. Others had more pronounced wet and dry cycles, creating environments that shifted between lush growth and open, dry ground. Plants and animals in these areas adapted to this variability, developing strategies to store water or survive periods of scarcity. Snow and ice, though rare, were not entirely absent. High mountains could still see snowfall during cooler periods. These patches of ice fed rivers as they melted, contributing to seasonal changes in water flow. The presence of even small amounts of ice in certain regions added another layer of complexity to the climate system. The sky also served as a pathway for long-distance connections. Migrating animals, especially birds, could use wind patterns and seasonal cues to move between regions. These movements linked distant ecosystems carrying seeds, nutrients, and even small organisms across the planet. Dust from dry regions could be lifted into the air and transported far away. When it settled, it added minerals to soils and oceans, sometimes boosting plant and plankton growth. This connection between land and sea carried through the atmosphere, tied together different parts of the Earth system in subtle ways. The daily cycle of light and dark shaped behaviour on a smaller scale. Dawn and dusk mark transitions for many animals, times when activity peaked or quieted. Temperature changes between day and night influenced when plants opened their flowers or closed their leaves, and when insects and mammals emerged to feed. The atmosphere was also a medium for sound. Calls, roars, and subtle noises travelled through the air, carrying information across forests and plains. The density and moisture of the air affected how far these sounds could go, shaping communication between individuals and groups. Over long periods, changes in the atmosphere left records in the natural world. Tree rings captured variations in growth linked to temperature and rainfall. Layers of sediment in lakes and oceans recorded shifts in dust, ash, and organic material carried by wind and water. These records, preserved in rock, offer glimpses into the patterns of ancient skies. The interplay between atmosphere and life was a continuous exchange. Plants altered the composition of the air by taking in carbon dioxide and releasing oxygen. Animals returned carbon dioxide through breathing. Microorganisms in soil and water processed gases in ways that influenced local and global conditions. This exchange created a feedback system. Changes in the atmosphere influenced where plants could grow. Changes in plant growth influenced how much carbon and oxygen moved between air and land. The system adjusted itself over time, sometimes smoothly, sometimes through more noticeable shifts. If you imagine standing in a Cretaceous landscape and looking up, you might see clouds moving slowly across a wide sky, their shapes changing without hurry. The sun would rise and set, casting long shadows, and then bathing the world in full light. A breeze might move through the leaves, carrying scents and sounds from places you cannot see. The sky, in that moment, would feel steady and familiar, even though its composition and behaviour were part of a much larger evolving system. It would be easy to forget how much was happening above, in layers of air stretching high, beyond any living creature's reach. This unseen activity guided the timing of rains, the spread of warmth, and the movement of winds that shaped the land and sea. It connected volcanic breath from below to sunlight from above, creating a space where life could exist and adapt. Long after clouds have drifted and storms have passed, there are signals of the planet's activity that leave no visible mark in the sky or on the ground, yet shape the world in ways just as real as rivers and mountains. During the Cretaceous, these quieter forces were constantly at work, guiding how the oceans rose and fell, how the land responded to unseen pressures, and how even the invisible shield around the planet shifted and changed. This was the deeper pulse of the Earth, a rhythm measured not in days or seasons, but in spans of time so long they blur into a single slow movement. One of these hidden forces was the magnetic field. Generated deep within the planet's core, this field arose from the motion of molten metal, swirling and flowing in patterns driven by heat escaping from the centre of the Earth. This movement created electrical currents, and those currents produced a magnetic shield that extended far out into space. Though no animal could see or feel it directly, this field played a crucial role in protecting the atmosphere from the constant stream of charged particles flowing outward from the sun. Without this invisible barrier, much of the planet's air could be stripped away over long periods, carried off into space by solar wind. During the Cretaceous, as today, the magnetic field acted like a quiet guardian. deflecting many of these particles and preserving the conditions that allowed water to remain liquid and life to persist on the surface. The magnetic field was not steady or fixed. Over geological time, it wandered and even reversed direction. North became south, and south became north, in events that unfolded over thousands of years. These reversals did not happen in a single moment. The field weakened, shifted, and then rebuilt itself in the opposite orientation. For animals living at the time, this change likely went unnoticed. For the rocks forming on the seafloor and in volcanic regions, however, it left a permanent record. As lava cooled, magnetic minerals within it aligned with the direction of the field. When the field later reversed, new layers of rock recorded the new orientation. Over time, this created patterns of alternating magnetic stripes, especially visible along mid-ocean ridges where new crust was constantly forming. These patterns are like a timeline written into the stone, marking the slow expansion of ocean basins and the steady passage of deep time. While the magnetic field shaped what happened above the atmosphere, the movement of the crust shaped what happened at the surface. Sea level during the Cretaceous did not stay fixed. It rose and fell in response to a combination of factors, some tied to climate, others to the shape of the ocean floor itself. One major influence was the rate at which new seafloor was created. Along the long ridges where tectonic plates pulled apart, magma rose and cooled, forming fresh crust. When these ridges were especially active, they took up more space on the ocean floor. This displaced water, pushing it outward and upward onto the continents. The result was higher global sea levels, with shallow seas spreading far inland. These inland seas transformed the geography of the world. Regions that are now far from any coastline were once covered by warm, shallow water. Islands formed where higher ground rose above the surface. Long winding shorelines created environments rich in life, where marine and land ecosystems overlapped. When the rate of seafloor spreading slowed, or when older, cooler crust sank deeper into the mantle, the volume of the ocean basins increased. Water drained back toward the coasts and sea levels fell. Land that had been underwater emerged, sometimes slowly, sometimes in steps marked by changes in sediment and erosion. New plains, river valleys, and coastal zones appeared, ready to be colonized by plants and animals. Climate played a role in this process as well. In a world without large ice caps, less water was locked away on land. Most of it remained in the oceans, contributing to generally high sea levels. Even so, small changes in temperature could influence how much water expanded or contracted, adding another layer of variation. These rising and falling seas left clear traces in the rock record. Layers of marine sediment, filled with shells and the remains of ocean life, appear far inland in many parts of the world. Above and below them, layers formed by rivers, deserts, or forests tell the story of times when the sea retreated. Together, these layers form a stacked history of shifting coastlines and changing environments. The movement of water across the land reshaped the surface in subtle ways. When seas advanced, waves and tides eroded rock and soil, smoothing coastlines and creating beaches, cliffs, and shallow shelves. When seas withdrew, rivers cut into newly exposed ground, carving channels and carrying sediment back toward the ocean. Over long periods, this back-and-forth motion sculpted the land into complex patterns of hills, plains, and valleys. Time itself became visible in these landscapes. Each layer of sediment, each buried soil horizon, and each band of fossil-rich rock marked a chapter in the planet's ongoing story. Though no living thing at the time could read this record, it was being written continuously beneath their feet. The idea of a pulse of time becomes clearer when you consider how these processes repeated. Sea levels rose, then fell. Magnetic fields flipped, then flipped back. Continents drifted, collided, and separated. Climate warmed and cooled in long cycles. These patterns did not follow a simple, regular schedule, but they did show a kind of rhythm driven by the flow of energy through the Earth system. life responded to these pulses in many ways. When seas advanced, marine species could spread into new areas. Shallow seas created corridors for movement and exchange between regions. When seas retreated, populations became isolated, evolving in different directions. Land animals gained new territories to explore, while coastal species had to adapt or move. Plants followed similar patterns. New land offered fresh ground for colonization. Soils formed on recently exposed surfaces, allowing forests and fields to take root. In some places, these new landscapes were temporary, destined to be covered again by the next rise in sea level. In others, they remained dry for millions of years, becoming the foundation for long-lasting ecosystems. The changing shape of the world influenced weather and climate. New coastlines altered wind patterns. Shallow seas affected how heat was stored and released. Mountain ranges raised by tectonic forces redirected air and rain. Each physical change fed back into the atmospheric and oceanic systems, creating a complex web of cause and effect. Even the distribution of magnetic minerals in the crust had subtle effects. While not directly influencing life, these minerals are part of the larger geological framework that shapes the strength and structure of the crust. The thickness and composition of the crust, in turn, influence how it responds to stress, where volcanoes form, and how mountains rise. The concept of deep time can be hard to hold in the mind. A single year is easy to imagine. 1,000 years stretches that sense. 1,000,000 years pushes it even further. The Cretaceous lasted tens of millions of years, long enough for entire mountain ranges to rise and wear down, for oceans to open and close, and for the magnetic field to reverse many times over. Within this span, the daily lives of animals and plants unfolded in ways that felt immediate and urgent to them. Finding food, avoiding danger, reproducing, and resting filled their awareness. The slow drift of continents and the invisible shifts in the planet's magnetic shield were far beyond their perception. Yet these distant processes shaped the stage on which their lives played out. Consider a shallow sea that gradually deepens as sea level rises. For generations of marine animals, the change might be barely noticeable. Each year, the shoreline moves a little farther inland. Each century, new habitats appear. Over 1,000,000 years, an entire region transforms from forested land into open water. The animals living there experience this as a slow migration, a steady adjustment to a changing world. On land, a similar story unfolds. A river that once flowed to the sea might, after a shift in land level or sea position, begin to carve a deeper valley instead. Floodplains become terraces, wetlands turned into dry ground. The plants and animals that rely on these features adapt, move, or disappear, replaced by others better suited to the new conditions. The magnetic field's reversals add another layer to this sense of time. These events do not leave visible scars on the landscape, but they are recorded in stone beneath the oceans and in volcanic rocks on land. They mark moments when the planet's internal dynamics reached a tipping point and reorganized themselves. These records allow a kind of dialogue between the present and the past. By reading the patterns in rock, scientists can reconstruct the timing of seafloor spreading, the movement of continents, and the pace of geological change. This understanding connects the world of today to the Cretaceous and beyond, revealing a continuity of process across immense spans of time. The pulse of the Earth is not a single beat, but many overlapping rhythms. Some are fast, like the daily rotation that brings day and night. Others are slower, like the yearly cycle of seasons. Still others move at a pace that can only be measured in millions of years, like the drift of plates and the wandering of the magnetic field. Together these rhythms create a layered sense of time, where moments of action and long periods of quiet change coexist. A storm can reshape a hillside in a day. A river can carve a canyon over thousands of years. A continent can cross an ocean basin over tens of millions. Life fits into this layered time in its own way. Species appear, change, and vanish. Ecosystems rise and fall, yet the deeper processes continue, providing a backdrop that is always shifting, even when it seems stable. If you imagine standing in a Cretaceous landscape and watching the sunset, the scene might feel peaceful and complete. The colours of the sky fade, the air cools, the sounds of day give way to those of evening. Nothing in that moment would suggest that the ground beneath you is slowly moving, that the magnetic field above you is wandering, or that the sea level nearby is part of a long global rise or fall. And yet, all of those things would be happening quietly and steadily, beyond the reach of immediate perception. They would shape the future of that place long after that single sunset had passed. This sense of a world guided by both visible and invisible forces brings us closer to the idea that the planet's story is one of continuous motion. Even when change seems slow, it is never absent. The Earth is always in the process of becoming something slightly different from what it was before. Long before anything in the sky gave reason for concern, the world of the Cretaceous moved along in the same patient way it always had, guided by seasons, shifting coastlines, and the slow breathing of the planet itself. Forests grew and fell. Oceans advanced and retreated. Animals followed the patterns they had learned over countless generations. From the perspective of any living creature, the future looked much like the past, stretching forward without a clear boundary or sign of change. Far beyond the reach of clouds and atmosphere, however, there were objects moving through space that did not belong to this steady rhythm. Fragments of rock and metal, shaped by collisions and gravity in the early history of the solar system, followed long looping paths around the Sun. Most of the time, these paths never crossed the orbit of Earth in any meaningful way. When they did, the meeting was often brief and harmless, a small meteor burning up in the upper air, leaving behind only a streak of light and a momentary glow. But not all of these travellers were small. Some were large enough to survive their passage through the atmosphere, reaching the surface with enough energy to leave a lasting mark. Over the planet's long history, these encounters had happened many times, shaping landscapes and, in some cases, altering the course of life itself. During the late Cretaceous, one such object was on a path that would eventually intersect with the Earth in a way no living thing could avoid. This object did not appear suddenly in the sky. It moved through space for millions of years, its course determined by the gravitational pull of the Sun and the planets. Its journey was quiet and distant, far removed from the daily concerns of any animal on Earth. The idea of an approaching end was not written into the clouds or carried on the wind. The planet continued, unaware. On the surface, life followed its familiar patterns. Herds moved across floodplains in search of fresh growth. Predators watched from the edges of forests and riverbanks. Birds and flying reptiles traced paths across the sky. In the oceans, schools of fish shifted with the currents, and large marine reptiles moved through warm, shallow seas. The connection between these scenes and a distant piece of rock in space was invisible. There was no signal, no gradual warning that something extraordinary was on its way. The Earth, in its long history, had absorbed countless small impacts without lasting effect. This time, however, the scale was different. As the object drew closer, it entered the influence of the planet's gravity. Its speed increased, pulled downward along a path that would carry it through the upper atmosphere and toward the surface. The energy it carried was enormous, far beyond anything produced by volcanic eruptions or earthquakes. It was the energy of motion built up over a long fall through the Sun's gravitational field. When it finally reached the atmosphere, the air in front of it compressed and heated, creating a brilliant glow. For a brief moment, the sky in that region would have held a light brighter than the Sun itself. The object did not slow enough to burn away. It continued, tearing through the air and reaching the surface in a fraction of a second. The place of impact lay in what is now the Yucatan region, near the edge of a shallow sea. The collision released an amount of energy equivalent to billions of tons of explosive force. The ground at the point of contact did not simply crack or crumble. It behaved like a liquid, flowing outward in a vast wave as rock was vaporized and thrown into the air. A crater formed, wide enough to span many kilometers, with a central peak created by the rebound of the compressed crust. The sea around the impact site was instantly displaced, sending waves racing outward across coastal regions. These waves, far larger than any ordinary storm surge, would have reached distant shorelines, reshaping coasts and flooding low-lying areas. The immediate effects near the impact were devastating. Everything within a wide radius was destroyed in an instant. Heat radiated outward, igniting vegetation and raising surface temperatures to extreme levels. The shockwave travelled through the ground and the air, flattening forests and disrupting landscapes far from the centre. Material ejected by the impact did not fall back to Earth right away. Much of it was blasted high into the atmosphere, and some even reached the edge of space. Fine particles of rock and dust spread around the globe, carried by high-altitude winds. These particles formed a kind of veil in the sky, blocking a significant portion of sunlight from reaching the surface. The days that followed would have felt different. The sky would have appeared dimmer, the light filtered and muted. Temperatures began to drop as less energy from the sun reached the ground. This cooling was not limited to the region of impact. It spread across the planet, creating a period of global change often referred to as an impact winter. Plants, which rely on sunlight to grow, were among the first to be affected. Reduced light slowed photosynthesis, weakening forests, fields, and plankton in the oceans. As plant growth declined, the animals that depended on those plants began to struggle as well. Herbivores found less to eat. Predators, in turn, found fewer healthy prey. In the oceans, the decline of plankton had wide-reaching effects. These tiny organisms form the base of the marine food web. When their numbers fell, everything above them felt the impact. Fish populations declined. Marine reptiles faced shortages of food. The balance that had supported the rich diversity of the Cretaceous seas began to shift. The atmosphere itself changed in other ways. The impact released gases from the vaporized rock and from the burning of vast areas of vegetation. Soot and ash joined the dust already in the air, further reducing sunlight and altering the chemistry of the sky. Acid rain may have fallen in some regions, as sulfur compounds and other gases mixed with water vapor. These changes did not happen all at once. The most intense effects were felt in the months and years immediately following the impact, but the consequences unfolded over longer periods as ecosystems struggled to adjust. Some species were able to survive in pockets where conditions remained more stable. Others could not find enough food or suitable environments and gradually disappeared. The idea of an end can make it sound like everything stopped at once. In reality, the transition was uneven. Some areas were hit harder than others. Some groups of animals declined rapidly, while others lingered for thousands of years. The planet did not fall silent in a single moment. Instead, its familiar patterns were disrupted, and a new set of conditions began to take shape. Small, adaptable animals had advantages in this changed world. Species that could eat a wide range of foods, that could shelter in burrows or water, or that could reproduce quickly were more likely to persist. Plants that could grow in low-light conditions or spread easily into open, disturbed areas found new opportunities. In this way, the impact did not just remove life, it also opened space. Ecosystems that had been dominated by certain groups became available for others to explore. The landscape, stripped in many places of its former complexity, became a canvas for new growth and new relationships. The falling object itself was gone, transformed into heat, dust, and altered rock. Its presence remained only in the crater it left behind and in the layers of sediment that recorded the sudden change in conditions. These layers, rich in a rare element called iridium, now serve as a marker for this moment in the planet's history. A thin line in the rock that separates what came before from what followed. From a human perspective, it is natural to focus on the drama of this event, the violence and the loss. From the perspective of the planet, it was one of many moments of rapid change in a long, ongoing story. The Earth had experienced massive volcanic eruptions, shifts in climate, and other impacts before. It would experience more in the future. What makes this moment stand out is how deeply it reshaped the living world. The long reign of dinosaurs on land came to an end, not because they were weak or failing, but because the conditions that supported their way of life changed faster than they could adapt. The skies, once filled with a mix of birds and flying reptiles, became quieter as pterosaurs disappeared. The seas lost many of their large reptilian inhabitants. On land, the absence of the largest herbivores and predators left open spaces in the structure of ecosystems. Yet life continued. In the sheltered corners of this changing world, mammals, birds, and other survivors began to expand into roles that had once been filled by others. Plants spread into areas cleared by fire and impact. The world did not return to what it had been, but it did not remain empty either. If you imagine standing somewhere far from the impact site in the years that followed, you might notice the difference in small ways. The sky might look slightly hazier, the air might feel cooler, the forests might be thinner, with more open ground between trees. Animals might be fewer, their movements less constant. Over time, though, signs of recovery would appear. New shoots would rise from the soil, insects would return to flowers, birds would nest in growing trees, rivers would carry fresh sediment to the sea, supporting new blooms of plankton. The end of an era, in this sense, was also the beginning of another. The world did not close a door and stop. It turned a page, moving into a chapter that would eventually lead to landscapes and life forms we recognise more easily today. It becomes easier to see the Cretaceous not just as a time that ended, but as a foundation for what followed. The patterns of climate, the spread of plants, the survival of small animals, and the reshaping of the land all fed into the next stage of the planet's story. After the sky dimmed and the first waves of change rolled across the land and sea, the world entered a stretch of time that did not announce itself with noise or movement, but with a kind of stillness. The great bodies that once filled the plains and forests were no longer shaping the daily rhythm of the surface. Instead, quieter forces took their place. Wind moved across open ground where dense vegetation had once stood. Water flowed through channels newly carved by erosion and flood. In many regions, the air itself seemed to carry a sense of pause, as if the planet was taking a slow breath after a sudden and powerful release of energy. The layers of ash and dust that settled from the sky did not form a uniform blanket. In some areas, they fell thick and heavy, coating leaves, soil and water surfaces in a pale film. In others, the particles were thinner, carried farther by high-altitude winds before drifting down. These differences mattered. Where ash was thick, it could smother plants, block light, and change the chemistry of the soil. Where it was lighter, it might mix into the ground and eventually add minerals that would support new growth. Rain played a role in reshaping this landscape. When the first storms passed through after the dust-filled skies began to clear, water washed ash into low-lying areas, rivers, and shallow seas. Streams ran grey for a time, carrying fine particles downstream. Sediment settled in layers, adding new chapters to the geological record. Floodplains, once shaped by plant roots and animal movement, were reworked by flowing water, creating new channels and deposits. The cooling of the planet, triggered by the reduced sunlight, lingered longer than the dust itself. Temperatures remained lower than before in many regions, and this influenced how quickly life could return. Plants that relied on warmth and long growing seasons struggled. Those that could tolerate cooler conditions or grow in low light found opportunities to spread. Seeds that had been buried in the soil, protected from the worst of the immediate effects, began to sprout. Some plants grew from underground roots or stems that had survived beneath the surface. In open, disturbed areas, fast-growing species appeared first, covering bare ground with low vegetation. These early colonizers stabilized the soil, reducing erosion and creating shade and organic matter that allowed other plants to follow. Forests did not return all at once. Instead, they rebuilt themselves in stages. Shrubs and small trees came before taller, slower-growing species. Over time, layers of vegetation formed again, though the mix of plants was often different from what had existed before. Flowering plants, which had already been spreading during the Cretaceous, found new space in these changing landscapes. Their ability to grow quickly and attract pollinators helped them establish themselves in areas where older plant groups had declined. Insects followed the plants. As soon as flowers, leaves, and decaying organic matter were available, small animals arrived to feed and reproduce. Beetles, flies, and other invertebrates became some of the most abundant forms of life in this early stage of recovery. Their presence supported birds and small mammals, which, in turn, helped spread seeds and control insect populations. The seas experienced their own version of this quiet rebuilding. Plankton populations, reduced by the dimmer light and cooler water, gradually recovered as sunlight returned. In areas where nutrients had been added by ash and erosion, blooms of microscopic life could be especially strong. These blooms formed the base for new marine food webs, drawing fish and other animals back into regions that had been quieter for a time. Near the coasts, changes in sediment and sea level reshaped shorelines. Some bays filled in with material carried by rivers. Other areas saw new inlets form where erosion cut into the land. These shifting boundaries created fresh habitats for marine and coastal species, adding variety to the recovering ecosystem. Mammals, which had already been living in the margins of the Cretaceous world, found new opportunities in this changed landscape. With fewer large predators and competitors, they could explore open spaces and new food sources. Some species remained small and cautious, continuing their nocturnal habits and burrowing lifestyles. Others began to grow larger over many generations, adapting to roles that had once been filled by reptiles and dinosaurs. Birds, too, expanded into a wider range of environments. The disappearance of flying reptiles left more room in the skies and along coastlines. Different forms of birds took advantage of this, spreading into areas where they had previously been less common. Their ability to fly allowed them to move between recovering regions, connecting distant ecosystems and helping life return more quickly. The soundscape of the world changed. The deep, heavy noises associated with large land animals were replaced by lighter, sharper sounds. The calls of birds, the movement of insects, and the rustle of small animals in vegetation became more prominent. The overall volume of life was lower at first, but it grew steadily as populations increased and new communities formed. Soils went through a period of adjustment as well. The mix of ash, decaying plant matter, and weathered rock altered nutrient levels. Microorganisms in the ground played a key role in processing this material, breaking it down into forms that plants could use. Fungi, bacteria, and other small life forms rebuilt the underground networks that support roots and help distribute water and minerals. Waterways became corridors of renewal. Rivers carried seeds, insects, and small animals from one area to another. Wetlands provided sheltered environments where young plants and animals could thrive. These moist regions often became centres of biodiversity, supporting a mix of land and aquatic species. The climate itself began to shift again. As dust and aerosols cleared from the atmosphere, more sunlight reached the surface. Temperatures slowly rose toward levels that supported broader plant growth. The balance of gases in the air adjusted as plants took in carbon dioxide and released oxygen, reinforcing the connection between the recovering biosphere and the sky above. This period of change was not uniform across the globe. Some regions recovered more quickly than others. Areas with rich soils, abundant water, and moderate climates saw faster growth. Places that were drier, colder, or more heavily affected by ash and erosion took longer to rebuild. The result was a patchwork of environments at different stages of recovery, creating a varied and dynamic world. The absence of the largest animals had noticeable effects on how the land looked and functioned. Without heavy bodies to trample vegetation and compact soil, Some areas became denser with plant growth. Trails and open spaces created by herds began to fill in. In other places, the lack of large herbivores allowed certain plants to grow taller and spread more widely than before. Predation patterns shifted as well. Smaller predators and omnivores became more important in shaping animal populations. The balance between insects, small mammals and birds created new forms of regulation within ecosystems. Instead of a few large species dominating energy flow, it moved through many smaller channels. The pace of evolution reflected these new conditions. With open niches and fewer established competitors, species that could adapt quickly found opportunities to diversify. Over thousands and then millions of years, this led to the emergence of new forms and behaviours, setting the stage for the world that would follow. The geological record of this time captures both disruption and renewal. Layers of sediment rich in ash and unusual chemical signatures mark the immediate aftermath of the impact. Above them, layers containing new types of plant pollen and animal fossils tell the story of recovery and change. These records are like a slow-motion film showing how a living system responds to a sudden shock and gradually finds a new balance. From a distance, this period might look like a simple decline followed by a steady rise. From within, it would have felt more uneven. A local population of plants might flourish while another struggled. A river valley might become a centre of life while a nearby plateau remained sparse. The world did not heal all at once. It adjusted piece by piece. Light itself took on a renewed importance. As skies cleared, the return of brighter days allowed plants to grow more vigorously. The changing angle of the sun through the seasons once again marked time in visible ways. Shadows lengthened and shortened, temperatures rose and fell. These familiar patterns provided a framework for the rebuilding of life. The oceans mirrored this gradual change. As surface conditions improved, deeper layers responded. Oxygen levels increased in some regions as water mixed, and plankton populations recovered. Coral-like organisms and reef builders began to establish new structures in shallow seas, creating habitats for fish and invertebrates. Currents carried life between regions, spreading species and mixing communities. A fish population that thrived in one recovering area could move along coastlines and into new waters, bringing energy and movement to places that had been quieter. The concept of silence in this period is relative. The world was never truly silent. Wind still moved through empty branches. Waves still broke along the shore. Insects still buzzed and crawled. But compared to the crowded, booming landscapes of the late Cretaceous, the early aftermath felt more open, more spacious. This openness allowed new relationships to form. Plants and animals encountered fewer established competitors. Interactions that might have been minor before could become central. A small mammal species might expand into a role as a primary seed disperser. A particular plant might become a dominant feature of a region simply because it arrived first and grew quickly. The long dawn of this new world was shaped by both chance and resilience. Which species survived the initial changes influenced the direction of everything that followed. Small differences in location, timing, or behaviour could ripple outward, shaping entire ecosystems over long periods. If you imagine standing in a recovering landscape, you might see a mix of old and new. Fallen trunks from trees that did not survive lie beside young plants reaching toward the light. Open ground stretches between patches of greenery. The air carries the smell of damp soil and fresh growth. Over time, these patches expand and connect. What was once a scattered pattern becomes a more continuous cover of vegetation. Animals follow these changes, moving into new areas, establishing territories, and creating the daily rhythms of feeding, resting, and moving that define a living world. This process does not rush. It unfolds at a pace that feels almost gentle, especially when set against the suddenness of what came before. Each season adds a layer. Each generation of plants and animals builds on the one before. The idea of a new world does not mean a complete break from the past. Many lineages continue, carrying traits and behaviours shaped during the Cretaceous into the future. The difference lies in how these traits are expressed, in the roles they play within a changed system. As the planet moves forward, the memory of the impact remains in the rocks. But life does not dwell on that memory. It grows, spreads, and adapts, responding to the conditions of the present rather than the events of the past. This steady return of activity, colour, and sound creates a sense of continuity. The Earth, even after profound change, continues its long pattern of renewal. The surface reshapes, the atmosphere adjusts. Living things find ways to fill the spaces that open up. From where we stand now, surrounded by a world of cities, fields, and carefully drawn maps, it can be easy to forget that the ground beneath our feet carries a much longer memory. The landscapes we move through every day are the latest shapes in a story that began far earlier than any written record, and the Cretaceous is one of the chapters that still leaves a quiet imprint on what we see, touch, and breathe today. Looking back across that stretch of time is not about peering into something distant and disconnected. It is about noticing how deeply the past is woven into the present. The most obvious traces appear in the rocks themselves. White cliffs, pale limestone hills, and layers of chalk found in many parts of the world are built from the remains of microscopic life that floated in warm Cretaceous seas. Each grain of these rocks was once part of a tiny shell, formed by an organism that lived, died, and sank to the ocean floor millions of years ago. When you see a cliff face or a stone wall made from this material, you're looking at the compressed memory of an ancient ocean, lifted out of the water and into the air by the slow movement of the Earth's crust. Oil and gas, so deeply tied to modern life, also trace their origins back to this time. The thick layers of plankton and plant matter that settled in Cretaceous seas and wetlands were buried under sediment, cut off from oxygen, and slowly transformed by heat and pressure into the fuels we now extract from deep underground. The energy that lights homes and moves vehicles today is, in a very real sense, sunlight captured by ancient life and stored away for millions of years. The shapes of continents still reflect the movements that were underway during the Cretaceous. The widening Atlantic, the northward journey of India, and the gradual separation of southern land masses set the stage for the world map we recognise now. Mountain ranges, coastlines, and ocean basins are the long-term results of those slow shifts. Even when standing on a quiet beach or looking across a flat plain, you're seeing a landscape that was guided into its current form by motions that began long before any human presence. The living world carries even more direct connections. Birds, which fill modern skies with sound and movement, are the most visible descendants of the feathered creatures that took to the air in the Cretaceous. Their bones, feathers, and flight patterns still reflect that deep history. When a bird lifts off from a branch or glides on a thermal current, it is repeating a behaviour refined over tens of millions of years. Flowering plants, now the dominant form of vegetation on land, also owe much of their success to that period. The partnerships they formed with insects, birds, and mammals during the Cretaceous laid the foundation for the rich variety of forests, fields, and gardens we see today. Fruits, seeds, and colourful blooms are not just decorations. They are the results of long-running relationships between plants and the animals that help them reproduce and spread. Mammals, including humans, carry the marks of a lineage that once lived in the shadows of giants. Traits like warm-blooded metabolism, varied teeth, and extended care for young were shaped during a time when survival depended on flexibility and caution. The ability to adapt to many environments, to learn and pass on behaviours, and to thrive in both open and sheltered spaces became part of the mammalian toolkit long before it was ever used to build societies or explore the planet. The oceans too reflect this deep connection. Many modern marine ecosystems are built on patterns established in the Cretaceous. Coral reefs, for example, trace their ancestry to earlier reef systems that flourished in warm, shallow seas. The flow of nutrients from land to ocean, the rise and fall of plankton populations, and the movement of currents that distribute heat and life around the globe all follow pathways shaped by the arrangement of continents and seas that emerged during that time. Even the air carries a kind of memory. The balance of gases in the atmosphere is part of a long cycle involving plants, oceans, rocks, and volcanic activity. The processes that regulated carbon dioxide and oxygen during the Cretaceous continue today, linking modern climate to ancient patterns of growth, decay, and geological change. The idea of a sudden ending, often associated with that period, can draw attention away from the continuity that followed. While the impact event marked a dramatic shift, it did not erase the past. Many lineages crossed that boundary, carrying traits, relationships, and roles into a changed world. The present is built not just on what disappeared, but on what persisted and adapted. Looking at fossils in a museum or a book can make the Cretaceous feel like a closed chapter, neatly separated from what came after. In reality, the line between then and now is more like a gradual blending. The same physical laws, the same cycles of water, carbon, and energy, and many of the same biological strategies have been in play ever since. The rocks beneath cities still move, if only by a few centimetres each year. The magnetic field still wanders and reverses over long spans of time. Sea levels still rise and fall in response to climate and the shape of the ocean floor. These processes did not end with the dinosaurs. They continue, shaping the future just as they shape the past. There is a quiet lesson in this continuity. The world we experience as stable and familiar is, on a deeper level, always in motion. Forests grow and retreat, coastlines advance and erode, species appear and fade. The scale of these changes often extends far beyond a single human lifetime, making them easy to overlook. At the same time, the Cretaceous offers a reminder of how interconnected everything is. A change in the sky can alter the growth of plants. A shift in ocean currents can influence climates far inland. A movement deep within the earth can reshape the surface and redirect the flow of water and life. The planet operates as a system of linked parts, where no single element stands alone. This perspective can make the present feel both smaller and larger at once. Smaller because human history occupies only a tiny fraction of the planet's timeline. Larger because our actions now become part of a story that will continue long after we're gone. The rocks and sediments forming today will be read by whatever comes next, just as we read the layers left behind by the Cretaceous. There is also a sense of resilience in this long view. Life has faced dramatic changes before and found ways to persist. That does not mean every species survives every challenge, but it does show that the living world has a remarkable ability to reorganize, adapt, and fill new spaces. Standing in a modern landscape, you can sometimes catch a glimpse of this deeper story. A fossil shell embedded in a stone wall, a bird's shadow passing over a field, a flowering plant pushing up through a crack in the pavement. These are small moments, but they're connected to a history that stretches back to warm seas, drifting continents and forests filled with unfamiliar shapes. Even the sense of time we use to measure our days is part of this broader flow. The rotation of the planet that brings night and morning is the same rotation that guided the seasons of the Cretaceous. The orbit around the sun that defines our year is the same path followed by the Earth when dinosaurs walked its surface. The difference lies not in the mechanics, but in the awareness. We have the ability to look back, to piece together stories from stone and bone, and to imagine worlds that no longer exist in their original form. This act of looking back does not change the past, but it can change how we see the present. The Cretaceous still whispers through the materials we use, the animals we share space with, and the landscapes we move across. It is present in the chalk beneath our feet, the birds in the trees, and the fuels drawn from deep underground. It is present in the shape of the continents and the patterns of wind and water that move across them. Listening to that whisper does not require special tools or training. It can begin with noticing a rock, a leaf, or a distant horizon, and recognizing that what you see is part of a much longer story. The ground you stand on was once shaped by ancient seas. The air you breathe has passed through countless living things before you. As this sense of connection settles, it becomes easier to feel part of a larger, ongoing process rather than separate from it. The planet is not just a setting for human activity, it is an active system, one that has been changing and adapting for billions of years. The Cretaceous, with its warm climates, drifting continents, rising flowers, feathered skies, and sudden turning point, is one of the ways we can glimpse that system in motion. It shows how worlds can feel stable and full, and yet still be part of a larger pattern of change. From this present moment, looking back across that long stretch of time, there is space for a quiet kind of curiosity. What will the rock forming today say about this era, millions of years from now? What traces of our forests, oceans, and cities will remain? The planet will continue, reshaping itself in ways that are both familiar and entirely new. Life will respond, adapt, and find new paths forward. The story that began long before the Cretaceous will keep unfolding, layer by layer, movement by movement. And as you rest with this thought, you can let the sense of deep time drift gently alongside your own sense of the present, connecting a quiet moment now to a vast, ongoing journey that stretches far beyond any single era, still moving, still becoming, still carrying the soft, persistent echoes of worlds that came before,